Welcome, dear traveler, to a journey through the vast, mysterious expanse of our universe. As you settle into comfort, allow your body to relax completely. Feel the weight of the day dissolving, your breathing becoming slow and steady, rhythmic like the pulse of distant stars. Tonight we embark on a voyage through 100 of the greatest mysteries that occupy the minds of astronomers, physicists, and dreamers. These are not questions that demand answers from you, but rather gentle invitations to wonder, to drift, to let your consciousness expand into the infinite darkness between galaxies. There is something profoundly calming about contemplating the cosmos. Our earthly concerns shrink to insignificance when we consider the scale of space and time. Your worries, your to-do lists, your anxieties, all of these fade like candlelight against the dawn when we turn our gaze upward to the stars. So close your eyes now if you haven't already. Breathe deeply. With each breath, imagine yourself rising gently above your bed, above your home, above the earth itself, until you're floating peacefully in the velvet darkness of space. Here, cradled by gravity and guided by curiosity, we begin our exploration. Let these mysteries wash over you like gentle waves. Some will spark recognition, others will feel strange and distant. None require your effort. Simply listen, drift, and allow the wonders of the universe to carry you softly into sleep. Mystery 1. The edge of the observable universe. Imagine, if you will, traveling outward from Earth at the speed of light. You pass the Moon in just over a second, Mars in minutes, and the edge of our solar system in hours. But to reach the edge of what we can observe would take 46 billion light-years of journey. This boundary isn't a wall or a barrier, but simply the limit of what light has had time to reach us since the beginning of the universe. But here's the mystery that lulls us deeper into contemplation. What lies beyond that edge? The universe didn't stop existing just because we can't see it. Beyond the observable horizon, space continues, perhaps infinitely. There may be galaxies, clusters, superclusters, and structures we will never, ever see. They exist in a realm forever sealed from our observation, not by distance alone, but by the fundamental nature of space-time itself. Some scientists suggest the universe may be infinite, extending forever in all directions. Others propose it might curve back on itself, finite yet unbounded, like the surface of a sphere. As you drift towards sleep, imagine what wonders might exist in those unreachable regions, forever hidden from human eyes. Mystery 2. The cosmic horizon problem. In the earliest moments after the Big Bang, different regions of the universe were too far apart to have ever exchanged information, even at the speed of light. Yet when we measure the cosmic microwave background radiation, the afterglow of the Big Bang, we find it remarkably uniform in all directions, with temperature variations of only 1 part in 100,000. How did regions of space that could never have communicated come to have almost exactly the same temperature and properties? It's as if you took 2 cups of water from opposite ends of the universe and found them at precisely the same temperature, despite never having been in contact. The leading explanation involves cosmic inflation, a period of exponential expansion in the first fraction of a second after the Big Bang. During this time, a tiny region of space, small enough to be in thermal equilibrium, expanded to become larger than our observable universe today. This theory soothes the paradox, suggesting that what appears to be separate regions were once close enough to exchange heat and energy. Yet mysteries remain. What drove inflation? What caused it to stop? And did it happen just once, or does it continue in regions beyond our cosmic horizon, creating endless bubble universes? Let these questions float through your mind like clouds across a summer sky, gentle and passing. Mystery 3. Dark flow. Deep in the cosmos, something strange is happening. Clusters of galaxies, spread across billions of light-years, all seem to be flowing in the same direction. as if drawn by some massive, unseen force beyond the edge of our observable universe. This phenomenon, called dark flow, suggests the presence of enormous structures outside what we can see, perhaps other universe remnants, or vast concentrations of matter left over from before inflation. These galaxy clusters are moving at over 2 million miles per hour, pulled toward a region of space we cannot observe. Imagine lying in a vast, dark ocean, feeling a current pulling you toward some distant destination you cannot see or comprehend. This is the situation of our galaxy cluster, caught in a cosmic river whose source and destination remain hidden. As you sink deeper into relaxation, picture yourself floating in this gentle current, carried along by forces ancient and mysterious. Mystery 4. The Great Attractor. In the direction of the constellations Hydra and Centaurus, some 200 million light-years away, something massive is pulling our galaxy, along with thousands of others, toward it at a speed of 1,400 miles per second. We call it the Great Attractor, though we cannot see it directly. It hides behind the zone of avoidance, a region where the disk of our own Milky Way blocks our view with dust and stars. What we know is that this region contains an anomalous concentration of mass, perhaps tens of thousands of times the mass of our galaxy. Is it a supervoid, a region of unusual dark matter density, or something else entirely? Astronomers have mapped the motion of galaxies around it, traced its gravitational influence. Yet the nature of this cosmic destination remains shrouded. Your body grows heavier now, more relaxed, as if pulled by its own gentle attractor toward the gravity of sleep. Mystery 5. Cosmic voids. Between the great walls and filaments of galaxies lie vast, empty regions called cosmic voids. These are not merely empty space, but enormous bubbles, sometimes hundreds of millions of light-years across, containing almost no galaxies at all. The largest known void, the KBC void, may be 2 billion light-years across. If you were somehow transported to the center of such a void, the night sky would be almost completely black, with perhaps only a handful of faint galaxies visible. The isolation would be profound. The nearest galaxy might be hundreds of millions of light-years away. What caused these voids to form? As the universe evolved, matter collapsed into filaments and walls under gravity's influence, leaving these great empty regions behind. Yet mysteries persist. Some voids seem to be expanding faster than they should. Others contain unexpected structure. The universe, it seems, has shaped itself into a cosmic foam, with matter collecting on the surfaces of these vast bubbles. As you breathe slowly, evenly, imagine the peace of floating in such a void, far from the chaos of galaxies, the turbulence of star formation, the violence of supernovae. Just silence, darkness, and the gentle whisper of the cosmic microwave background. Mystery 6. The Axis of Evil. When scientists mapped the cosmic microwave background with exquisite precision, they expected to find completely random fluctuations in every direction. Instead, they discovered something unexpected, a subtle alignment in the largest temperature variations, all seeming to point in the same direction. This alignment, nicknamed the Axis of Evil by frustrated cosmologists, shouldn't exist according to our best models of the universe. It suggests that the universe might have a preferred direction or orientation, something that violates our assumption of cosmic isotropy, the idea that the universe looks the same in all directions. Is this a statistical fluke, an error in our measurements? Or does it hint at something deeper, perhaps the rotation of the universe, or the influence of structures from before the Big Bang? The mystery remains unsolved, a cosmic asymmetry in what should be perfect symmetry. Let your mind release the need for perfect symmetry. In sleep, as in the universe, unexpected patterns emerge, and that is perfectly fine. Mystery 7. The Eridanus supervoid. In the constellation Eridanus lies a cold spot in the cosmic microwave background, a region that's significantly cooler than its surroundings. The likely explanation is a supervoid, an enormous underdense region of space containing far less matter than average. But this void is unusual. It's larger and more underdense than our theories predict should be possible. The cold spot it creates is about 5 times larger than expected, suggesting either that our understanding of cosmic structure formation is incomplete, or that something strange happened in that region of space. Some speculative theories suggest this could be evidence of a collision with another universe, a scar left from when our cosmic bubble bumped against another. Others propose it might be a region where the properties of dark energy differ from the rest of the universe. The truth remains elusive, floating just beyond our grasp, like the fading edges of a dream. Mystery 8. Galaxy rotation. Problem. When astronomers measure how fast galaxies rotate, they find something puzzling. The outer regions of galaxies spin much faster than they should, based on the visible matter alone. Stars at the edges should be moving more slowly, or they would fly apart, yet they orbit at speeds suggesting far more mass than we can see. This observation was one of the first compelling pieces of evidence for dark matter, an invisible form of matter that outweighs ordinary matter by 5 to 1. Galaxies, it seems, are embedded in vast halos of this mysterious substance, which provides the gravitational glue holding them together. Yet the mystery deepens. Some galaxies seem to have more dark matter than others. A few appear to have almost none at all. The relationship between visible and dark matter varies in ways we don't fully understand, and what dark matter actually is remains one of the most profound questions in physics. Feel your thoughts slowing, like the rotation of a distant galaxy, spinning gently, held together by invisible forces, drifting peacefully through the night. Mystery 9. The missing satellites problem. Our galaxy, the Milky Way, should have thousands of small satellite galaxies orbiting it, according to computer simulations of cosmic structure formation. Yet we observe only about 50. Where are all the missing satellites? Several explanations have been proposed. Perhaps the missing satellites are there, but made almost entirely of dark matter, with so few stars that we can't detect them. Or maybe the process of galaxy formation suppresses star formation in small dark matter halos, leaving them invisible. Some theories suggest that our understanding of dark matter itself needs revision. This mystery reminds us how much we still don't know about galaxy formation, dark matter, and the evolution of cosmic structure. The universe holds secrets in every scale, from the smallest satellite galaxies to the largest superclusters. Your breathing deepens. The mystery of missing things doesn't trouble you. In sleep, we let go of what we cannot find, trusting in the darkness. Mystery 10. The Hubble tension. The universe is expanding, but how fast? When we measure the expansion rate, called the Hubble constant, using nearby observations, we get one answer. When we measure it using the cosmic microwave background and early universe observations, we get a different answer. The discrepancy is statistically significant and has persisted despite increasingly precise measurements. This tension suggests either unknown systematic errors in our measurements or, more intriguingly, new physics. Perhaps dark energy evolved over time. Maybe the universe's expansion isn't uniform, or our cosmological model needs fundamental revision. This mystery excites astronomers because it might be pointing us toward the next breakthrough in our understanding of the cosmos. Sometimes the most interesting questions emerge not from complete ignorance, but from slight inconsistencies in what we thought we knew. Mystery 11. What is dark matter? Imagine that everything you've ever seen, every person, tree, building, planet, and star, makes up less than 5% of the universe. The rest is invisible, detectable only through its gravitational effects. This is the reality we face. Dark matter neither emits nor absorbs light. It doesn't interact with electromagnetic radiation in any way we've detected. It passes through ordinary matter as if we weren't even there. Yet its gravity shapes galaxies, bends light, and determines the large-scale structure of the cosmos. We know dark matter exists because galaxies rotate too fast. Galaxy clusters are more massive than their visible matter suggests, and gravitational lensing reveals invisible mass-bending spacetime, but what it actually is remains unknown. Is it composed of particles we've never detected? Primordial black holes? Something stranger still? Dozens of experiments around the world are searching for dark matter particles deep underground to shield them from cosmic rays. So far, they've found nothing. The invisible substance that dominates our universe remains frustratingly elusive. As you drift deeper into rest, imagine yourself becoming less substantial, more ephemeral, like dark matter itself. Present but intangible, influential but invisible, there but not there. Mystery 12. Dark matter. Candidate scientists have proposed many possible identities for dark matter. The most popular candidate is called a WIMP, a weakly interacting massive particle. These hypothetical particles would barely interact with ordinary matter, making them extremely difficult to detect, yet they could account for dark matter's observed properties. Another candidate is the axion, a much lighter particle predicted by certain theories of particle physics. Axions might be produced in tremendous quantities, filling the universe with a sea of these nearly massless particles. Primordial black holes, formed in the early universe rather than from stellar collapse, represent another possibility. Perhaps dark matter isn't exotic particles at all, but simply black holes we haven't detected, scattered throughout space. Then there are sterile neutrinos, modified gravity theories, self-interacting dark matter, and even more exotic possibilities involving extra dimensions or supersymmetry. Each hypothesis has its proponents, its predicted signatures, and its experimental searches. The truth is, we're searching in the dark for darkness itself, guided only by its gravitational whisper. Your mind quiets like an underground detector, waiting in stillness for a signal that may or may not come. Mystery 13. The nature of dark energy. If dark matter is mysterious, dark energy is even more so. This invisible force makes up about 68% of the universe and appears to be causing the expansion of space to accelerate. Discovered in 1998 by observing distant supernovae, dark energy was completely unexpected. According to our understanding, gravity should slow the universe's expansion, not speed it up. Yet observations clearly show that galaxies are receding from each other at an accelerating rate. What could cause this? The simplest explanation is that empty space itself has energy, a cosmological constant, an intrinsic property of the vacuum. But calculating what this energy should be from quantum mechanics gives an answer that's wrong by a factor of 10, to the power of 120, perhaps the worst prediction in the history of physics. Other theories propose that dark energy is dynamic, changing over time, what physicists call quintessence. Or perhaps our theory of gravity breaks down on cosmic scales, and no dark energy exists at all. The mystery remains wide open. Feel your body lightening, as if anti-gravity were gently pulling you upward, floating you effortlessly between wake and sleep. Mystery 14. The cosmological constant problem. Why is there something rather than nothing? Quantum mechanics tells us that even empty space isn't truly empty. Virtual particles constantly pop into existence and annihilate, creating a seething foam of quantum activity. This quantum vacuum should have energy, and that energy should behave like a cosmological constant. The problem is that when physicists calculate how much vacuum energy there should be, they get an enormous value, so large that the universe should have blown itself apart in a fraction of a second after the Big Bang. Yet we observe a cosmological constant 120 orders of magnitude smaller. This is the cosmological constant problem, sometimes called the vacuum catastrophe. Something must be canceling out most of the vacuum energy, leaving only a tiny residue that we observe as dark energy, but we have no idea what that something is or why the cancellation is so exquisitely precise. Some physicists suggest that in a multiverse, only universes with tiny cosmological constants allow stars, planets, and observers to exist. We find ourselves here because everywhere else is lifeless. Others seek a deeper principle that sets the vacuum energy to its observed value. The mystery invites you to let go of the need for complete understanding. Some questions float unanswered, and that's okay. Sleep comes regardless. Mystery 15. Modified gravity. Theories. What if dark matter and dark energy don't exist at all? What if gravity simply behaves differently than Einstein's general relativity predicts, especially over very large distances or in extremely weak gravitational fields? Several modified gravity theories have been proposed. MOND. Modified Newtonian dynamics alters the law of gravity at low accelerations and can explain galaxy rotation curves without dark matter. TVS and other theories attempt to make similar modifications while maintaining consistency with general relativity's successful predictions. These theories face challenges. They must explain all the phenomena attributed to dark matter, galaxy rotation, gravitational lensing, cosmic structure formation, using only modified gravity. Most struggle to explain observations from galaxy clusters in the cosmic microwave background without invoking some dark matter. Yet they persist because they address a deep discomfort. We're explaining the universe's behavior by invoking substances we've never detected. Perhaps the answer is simpler, not new particles, but new physics governing gravity itself. Your thoughts drift like gravitational waves through space-time, no longer bound by rigid theories, free to explore possibility. Mystery 16. Dark matter halos. Every galaxy, our Milky Way included, sits at the center of an enormous halo of dark matter extending far beyond the visible stars. These halos are not uniform spheres, but complex structures, possibly containing subhalos, streams, and clumps. Computer simulations predict that dark matter halos should contain far more small-scale structure than we observe. This discrepancy, called the cuspy halo problem and the missing satellite problem, hints that we might not fully understand how dark matter behaves or how galaxies form. Some solutions propose that dark matter particles interact with each other, smoothing out the densest regions. Others suggest that feedback from star formation can reshape the dark matter distribution. Or perhaps our simulations miss important physics. The halos themselves might have formed in fascinating ways. As the universe evolved, smaller dark matter clumps merged to form larger ones in a hierarchical process that built up cosmic structure from the bottom up. Our galaxy's halo might contain streams of dark matter from ancient, disrupted satellite galaxies. Imagine yourself surrounded by an invisible halo, a cocoon of unseen matter cradling you gently, keeping you safe as you drift deeper into sleep. Mystery 17. Dark energy's equation of state. The behavior of dark energy is characterized by its equation of state, the relationship between its pressure and density. For a true cosmological constant, this ratio equals -1, a strange value that means dark energy's pressure is negative, causing space to expand. But is dark energy truly constant, or does it evolve over time? Astronomers are measuring the equation of state at different cosmic epochs, looking for any deviation from -1. Even a small change would revolutionize our understanding. If the equation of state is less than -1, we'd have phantom energy, which would eventually tear apart galaxies, solar systems, atoms, and even space-time itself in a big rip. If it's greater than -1, dark energy might dilute over time, eventually becoming negligible. Current observations are consistent with a cosmological constant, but uncertainties remain. Future surveys, mapping billions of galaxies and measuring cosmic expansion with unprecedented precision, will narrow down the possibilities. Your consciousness expands and contracts with each breath, constant yet changing, like dark energy filling the cosmos. Mystery 18. Phantom energy. Imagine a form of energy so strange that it becomes more dense as the universe expands. This is phantom energy, a hypothetical form of dark energy with an equation of state parameter less than -1. If phantom energy exists, the universe's fate would be dramatic and violent. The accelerated expansion would intensify over time, becoming stronger and stronger. Eventually, the expansion would overwhelm gravity on all scales. Galaxy clusters would be torn apart first, then galaxies themselves, then star systems. As the Big Rip approached, the expansion would tear apart planets, then molecular bonds, then atoms themselves. In the final moment, space-time itself would be ripped apart. The universe would end not in cold darkness or fiery collapse, but in a cataclysmic shredding of reality itself. Fortunately, current observations suggest our universe's dark energy is not phantom energy. The equation of state appears to be very close to -1, consistent with a cosmological constant. But we cannot yet rule out phantom energy entirely. Let the thought of cosmic endings fade away. Tonight, there is no ending, only gentle transition from waking to sleeping, as natural and peaceful as starlight. Mystery 19. Quintessence. Rather than being constant, dark energy might be dynamic, evolving as the universe ages. This hypothetical form of dark energy is called quintessence, after the ancient concept of a fifth element beyond Earth: water, air, and fire. Quintessence could be a scalar field, similar to the inflaton field thought to drive cosmic inflation, but with much weaker energy density. As the universe expands, this field slowly rolls down its potential energy curve, changing the amount of dark energy over cosmic time. Different quintessence models predict different evolutionary histories. In some, dark energy was negligible in the early universe and only became important recently. In others, dark energy was once stronger and is now weakening. Each possibility leads to different predictions for cosmic structure formation and the universe's ultimate fate. Observationally distinguishing quintessence from a cosmological constant is challenging but possible. By precisely measuring the universe's expansion history at different epochs, astronomers hope to detect the subtle signature of evolving dark energy. Your breathing is quintessence itself, dynamic yet regular, changing yet familiar, carrying you through the epochs of sleep. Mystery 20. The coincidence problem. Here's a curious puzzle. Dark energy and dark matter have very different properties and origins, yet today they contribute roughly comparable amounts to the universe's total energy density. Dark matter outweighs dark energy by only about a factor of 2. This seems like a remarkable coincidence. In the early universe, dark matter dominated completely. In the far future, dark energy will dominate overwhelmingly. We happen to live in the brief cosmic epoch when they're almost balanced. Why? One possibility is pure chance. We're simply lucky to live at this particular time. Another is the anthropic principle. Observers can only exist during epochs when dark matter has formed galaxies, but dark energy hasn't ripped them apart. We observe this coincidence because it's necessary for our existence. Or perhaps there's a deeper connection between dark matter and dark energy that we don't yet understand. Some theories propose that they're different manifestations of the same underlying phenomenon, which would explain their current balance. The coincidence of this moment, your body perfectly poised between waking and sleeping, consciousness and dreams, needs no explanation. It simply is, as natural as starlight. Let go of tension now. Feel it draining from your muscles, your mind, your consciousness. Unlike cosmic tension, your tensions can dissolve completely, leaving only peace. Mystery 21. Inside a black hole. Cross the event horizon of a black hole, and you've passed the point of no return. Not even light can escape. But what happens to you as you fall inward toward the singularity? According to general relativity, you'd experience spaghettification. Tidal forces would stretch you lengthwise and compress you sideways as the gravitational field becomes increasingly intense. For a stellar mass black hole, you'd be torn apart long before reaching the event horizon. For a supermassive black hole, you might survive crossing the horizon intact, but your fate would be sealed nonetheless. Inside the horizon, space and time exchange roles in a sense. Just as you can't avoid moving forward in time outside a black hole, you can't avoid moving toward the singularity once inside. It's not a place in space you fall toward, but a moment in your future you inevitably reach. At the singularity, our equations break down. Density becomes infinite, space-time curvature becomes infinite, and general relativity can no longer describe what happens. Perhaps quantum gravity takes over. Perhaps singularities don't actually exist, replaced by some exotic quantum structure. No information escapes to tell us. The interior of a black hole remains utterly inaccessible to external observation. Let this mystery cradle you like the darkness cradles starlight, completely, absolutely, without question. Mystery 22. The information paradox. Quantum mechanics says information cannot be destroyed. General relativity says anything that falls into a black hole is lost forever. When Stephen Hawking showed that black holes evaporate, emitting radiation until they completely vanish, this contradiction became acute. Where does the information go? If information is destroyed, quantum mechanics is violated. If it's preserved somehow, we need to understand how it escapes the black hole, which seems to violate general relativity. This is the black hole information paradox, one of the deepest problems in theoretical physics. Proposed solutions are exotic and mind-bending. Perhaps information is encoded in subtle correlations in Hawking radiation. Maybe it's stored on the event horizon in a holographic form. Or possibly black hole evaporation leaves behind a remnant containing all the information. Some theories propose that information is released during the final moments of evaporation. Others suggest that the paradox reveals limitations in our understanding of quantum mechanics or general relativity or both. The debate continues, with profound implications for quantum gravity and the nature of reality itself. Information about your day dissolves now, not destroyed, but transformed, integrated into the fabric of dreams, where logic gives way to symbol and narrative. Mystery 23. Hawking radiation. Quantum mechanics allows particle-antiparticle pairs to spontaneously appear from vacuum fluctuations, briefly existing before annihilating each other. Near a black hole's event horizon, something remarkable can happen. One particle falls in while its partner escapes, creating the appearance that the black hole is radiating. This is Hawking radiation, named after Stephen Hawking, who predicted it in 1974. The black hole slowly loses mass through this process, eventually evaporating completely over unimaginably long timescales. A solar mass black hole would take 10 to the power of 67 years to evaporate, far longer than the current age of the universe. Yet Hawking radiation has never been directly observed. Black holes are so cold, their temperature inversely proportional to their mass, that the radiation is completely swamped by other sources. only microscopic black holes, if they exist, would be hot enough to detect. The prediction of Hawking radiation connected quantum mechanics, general relativity, and thermodynamics in profound ways. It suggested that black holes have temperature and entropy, and that they're not completely black after all. These insights have guided theoretical physics for decades. Feel warmth radiating from your body, gentle and constant, like a black hole's whisper to the universe, barely perceptible but definitely there. Mystery 24. Naked singularities. The cosmic censorship hypothesis, proposed by Roger Penrose, states that singularities are always hidden behind event horizons, never visible to external observers. But is this actually true, or could naked singularities exist? A naked singularity would be a point of infinite density visible from the outside, not cloaked by an event horizon. Such an object would be bizarre beyond imagination, potentially breaking causality and making physics unpredictable. If you could observe a naked singularity, you might see effects violating everything we know about how the universe works. Various scenarios could theoretically create naked singularities. A spinning black hole might spin fast enough that its event horizon disappears, or a collapsing object might form a singularity without creating an event horizon. However, whenever these scenarios are carefully analyzed, some mechanism seems to prevent the naked singularity from forming. Whether naked singularities can truly exist remains unresolved. If cosmic censorship is absolute, nature has a way of always hiding singularities from view. If not, the universe might be far stranger than we imagine. Your inner thoughts remain modestly censored by the growing fog of sleep, visible to you alone, private and protected like a singularity behind its horizon. Mystery 25. Primordial black holes. Most black holes form from collapsing stars, but in the early universe's extreme conditions, density fluctuations might have created black holes directly. These primordial black holes could range from microscopic to thousands of solar masses. If they exist, primordial black holes could solve several mysteries at once. They might constitute some or all of dark matter. They could explain the unexpectedly large black holes found in the early universe. Tiny primordial black holes, evaporating now via Hawking radiation, might produce detectable signals. The challenge is finding them. Intermediate mass primordial black holes might betray their presence through gravitational lensing or by disrupting star clusters. Massive ones might be detected through their gravitational waves, but proving a black hole is primordial rather than stellar in origin is difficult. Recent observations have rekindled interest in primordial black holes. LIGO's detection of merging black holes with unusual masses has led some to speculate about primordial origins. The theory remains speculative but tantalizing. Imagine your thoughts as primordial fluctuations, some collapsing into dreams, others evaporating into the quantum foam of near sleep, each following its natural path. Mystery 26. Supermassive black hole formation. At the center of nearly every large galaxy lurks a supermassive black hole containing millions to billions of solar masses. Our Milky Way's central black hole, Sagittarius A star, masses 4 million suns. The largest known black holes exceed 10 billion solar masses. How did these monsters form? Stellar mass black holes grow slowly by accreting matter, and there hasn't been enough time since the Big Bang for them to grow to supermassive scales through accretion alone. Yet we observe supermassive black holes in galaxies less than 1 billion years after the Big Bang. Several formation scenarios have been proposed. Perhaps massive stars in the early universe, hundreds of times more massive than today's stars, collapsed directly into large black holes. Or maybe dense star clusters collapsed collectively, forming intermediate mass black holes that merged and grew. Another possibility involves direct collapse of primordial gas clouds. Under special conditions, a cloud might collapse without fragmenting into stars, creating a black hole of 10,000 to 100,000 solar masses immediately. These seeds could then grow through mergers and accretion. The mystery deepens with recent observations showing that supermassive black holes and their host galaxies appear to evolve together. The black hole's mass correlates tightly with the galaxy's central stellar bulge, suggesting a profound connection between galaxy formation and black hole growth. Your consciousness, like a forming galaxy, gathers its scattered thoughts into a coherent center, organizing itself around the gravity of impending sleep. Mystery 27. Black Hole. Entropy. Black holes are the universe's most efficient information storage devices. Stephen Hawking and Jacob Bekenstein showed that a black hole's entropy, its information content, is proportional to the area of its event horizon, not its volume. This seems strange. For ordinary objects, entropy depends on volume, as you'd expect. A box twice as large can hold twice as many particles in different arrangements. But for black holes, the relationship is with surface area, suggesting that all the information about what fell into a black hole is somehow encoded on its two-dimensional surface. This insight led to the holographic principle, one of the most profound ideas in modern physics. Perhaps all the information in a three-dimensional region can be encoded on its two-dimensional boundary. Our universe itself might be holographic, with everything we experience emerging from information encoded on a distant cosmic boundary. The formula for black hole entropy, involving fundamental constants from quantum mechanics, thermodynamics, and gravity, hints at deep connections between these areas of physics. It's one of the few equations that successfully combines quantum mechanics and general relativity. Let your mind's complexity fold down into simpler forms, information compressed, boundaries dissolving, awareness becoming surface thin as sleep approaches. Mystery 28. The Firewall Paradox. Recent theoretical work has revealed a new puzzle about black holes. If information is preserved in Hawking radiation, as quantum mechanics requires, then particles near the event horizon must be highly correlated with previously emitted radiation. But this seems to require that the region just inside the horizon be a firewall of high-energy particles that would incinerate anything crossing it. This contradicts general relativity's equivalence principle, which states that an observer crossing the event horizon should notice nothing special, no firewall, no barrier, just smooth space-time. You can't have both information preservation and smooth horizon crossing, yet both seem necessary. The firewall paradox has spawned numerous proposed solutions. Maybe the equivalence principle breaks down at event horizons. Perhaps space-time is not smooth at quantum scales, or possibly our understanding of quantum entanglement needs revision. Some physicists suggest that observers falling into black holes would indeed encounter firewalls, making black holes far more violent than previously thought. Others propose that the paradox reveals limitations in how we apply quantum mechanics to gravity. The question remains open, inviting us to reconsider our most basic assumptions about space, time, and information. Your assumptions about remaining awake prove similarly unstable, breaking down as you approach the event horizon of sleep. Mystery 29. Ring singularities. When a black hole rotates, its singularity takes on a different character. Instead of a point, it becomes a ring, a circle of zero thickness with bizarre properties. The mathematics describing rotating black holes, called Kerr black holes, suggest that you could potentially pass through this ring singularity. What would you find on the other side? The equations permit strange solutions, negative space, regions where gravity is repulsive, even paths to other universes or other times. You might emerge into a different universe entirely, or into the past of our own universe. Of course, these mathematical possibilities might not correspond to physical reality. Quantum effects, not included in general relativity, might prevent ring singularities from forming, or instabilities might destroy anything attempting to pass through. The interior geometry of rotating black holes remains purely theoretical. We can never observe it from outside, and no information can return from inside. These regions exist in our equations, but perhaps nowhere in the physical universe. Imagine passing through a ring, from waking to sleeping, from one mode of consciousness to another, through a singularity where the laws of waking thought no longer apply. Mystery 30. White holes. General relativity's equations permit a mirror image of a black hole. A white hole, a region from which matter and light can escape but into which nothing can enter. While black holes pull everything toward their singularity, white holes would push everything away. Do white holes exist? We've never observed one, and there are good reasons to think they might be impossible. While mathematically valid solutions to Einstein's equations, white holes appear to be unstable and would likely collapse immediately, either evaporating or converting into black holes. Some cosmologists have speculated that the Big Bang itself might have been a white hole, a singular event from which our entire universe emerged. Others suggest that when a black hole evaporates completely, it might leave behind a white hole remnant. There's also speculation that black holes and white holes could be connected by wormholes, creating passages through space-time. An object falling into a black hole might emerge from a white hole elsewhere or elsewhen, though this possibility seems to be ruled out by practical considerations. White holes remain mathematical curiosities, beautiful solutions to Einstein's equations that may have no physical realization. Like dreams, they exist perfectly in the realm of mathematics, questionable in the realm of reality. Mystery 31. What came before the Big Bang? The Big Bang was not an explosion in space, but an expansion of space itself. Time and space began together, according to general relativity, but this raises a profound question. What came before? Asking what came before time began might be meaningless, like asking what's north of the North Pole. If time itself started with the Big Bang, there was no before. Yet our intuition rebels against this idea. Surely something must have existed. Surely some cause must have preceded this effect. Some theories propose that our universe emerged from a pre-existing state. Perhaps it budded off from a parent universe in a multiverse. Maybe it arose from quantum fluctuations in a primordial vacuum. Or possibly time is cyclic, with Big Bangs following big crunches in an eternal sequence. String theory suggests the possibility of a pre-Big Bang phase, a contracting universe that bounced into expansion. Loop quantum gravity proposes that the Big Bang was actually a big bounce, the universe collapsing and rebounding from a previous cosmic cycle. We may never know what, if anything, preceded our universe's beginning. The question pushes against the limits of scientific inquiry, where physics meets metaphysics. Let the question dissolve, like time itself, unmeasured and unmeasurable in the space before sleep. Mystery 32. The flatness problem. The universe appears to be geometrically flat on large scales, meaning parallel lines, remain parallel, and the angles of triangles sum to 180 degrees, but this flatness is extremely improbable and requires fine-tuning. If the universe's density had been even slightly different in the early universe, 1 part in 10 to the power of 60 different, it would have quickly become obviously curved, either collapsing back on itself or expanding so rapidly that no structures could form. Yet we observe a universe very close to the critical density separating these fates. Why is the universe so precisely balanced? Cosmic inflation provides an answer. During inflation's rapid expansion, any initial curvature would have been stretched to imperceptibility, making the observable universe appear flat regardless of its global geometry. But this shifts the question, why did inflation occur with just the right properties to create a flat universe? Some cosmologists invoke the anthropic principle. Only in flat or nearly flat universes could observers evolve to ask the question. Others seek a deeper physical principle that requires flatness. The mystery reminds us that our universe's properties, which seem natural to us, might be extraordinarily special, balanced on a knife edge of possibility. Your body finds its own flat geometry now, stretched out comfortably, balanced between waking and sleep. Mystery 33. Matter-antimatter asymmetry. For every particle there exists an antiparticle with opposite charge. When they meet, they annihilate, converting their mass to energy. In the early universe, particles and antiparticles should have been created in equal numbers. They should have completely annihilated each other, leaving a universe of pure energy with no matter at all. Yet here we are, made of matter, in a universe dominated by matter. For every billion particle-antiparticle pairs that annihilated, one extra matter particle survived. That tiny asymmetry, 1 part in a billion, accounts for all the matter we see, every star, planet, and person. What caused this imbalance? The answer must involve processes that violate certain symmetries in particle physics. The standard model includes some symmetry violation, but not enough to explain the observed matter dominance. Theories beyond the standard model propose new particles and interactions that could generate the necessary asymmetry. Perhaps it occurred during the electroweak phase transition, or during the decay of heavy particles in the first moments after the Big Bang, or through some mechanism we haven't yet imagined. The question of why we exist, rather than just photons and emptiness, remains one of cosmology's deepest mysteries. Your existence, too, is a kind of asymmetry, a temporary imbalance that will eventually resolve back into equilibrium, but not tonight, not yet. Mystery 34. The first moments after the Big Bang. The first second after the Big Bang contained more physics than the entire subsequent history of the universe. Temperature and density were so extreme that our understanding becomes increasingly uncertain as we approach time zero. At 1 Planck time, 10 to the power of minus 43 seconds, quantum effects dominate gravity, and our theories break down completely. We simply don't know what happened during this era. Quantum gravity, still undiscovered, would be needed to describe it. By 10 to the power of minus 35 seconds, cosmic inflation may have occurred, expanding the universe exponentially. By 10 to the power of minus 10 seconds, quarks and gluons condensed into protons and neutrons. By 1 second, the universe had cooled enough for neutrinos to decouple and travel freely. Each of these transitions, inflation ending, symmetries breaking, particles condensing, shaped the universe we inhabit. Different outcomes at any stage would have produced radically different universes, perhaps devoid of stars, galaxies, or life. We piece together this history from particle physics experiments, cosmological observations, and theoretical calculations, but vast uncertainties remain. The first moments contain the seeds of everything, compressed into intervals too brief to comprehend. Time compresses for you too, hours of night passing in what will seem like moments, the duration of sleep mysterious and elastic. Mystery 35. Inflation theory questions. Cosmic inflation elegantly solves several problems in cosmology, but it raises new questions. What field drove inflation? What determined when it started and stopped? Why did inflation produce such specific conditions? The inflaton field, hypothetical quantum field responsible for inflation, has never been directly detected. We don't know what its properties are, how it coupled to other fields, or why it existed in the first place. Different inflation models make different predictions about the universe's large-scale structure and gravitational wave background. Ongoing observations are testing these predictions, narrowing the range of viable models. But dozens of inflation variants remain consistent with current data. Some cosmologists question whether inflation happened at all, proposing alternative mechanisms to explain the universe's observed properties. Others embrace inflation but puzzle over what caused it, seeking a deeper theory. Perhaps the ultimate question is, if inflation created our observable universe from a tiny patch of space, what about the rest of space? Did inflation end everywhere simultaneously, or does it continue in other regions, creating endless bubble universes? Questions multiply like quantum fluctuations. Let them go. The mystery of why anything exists can wait for tomorrow's contemplation. Mystery 36. The multiverse hypothesis. If inflation is eternal, never completely ending everywhere at once, it would create an infinite number of bubble universes, each with potentially different physical laws and constants. Our universe would be just one bubble in an infinite foam. This multiverse hypothesis is controversial. If other universes are completely disconnected from ours, can we meaningfully say they exist? Can a theory that predicts unobservable entities be scientific? Proponents argue that the multiverse naturally explains why our universe's constants seem fine-tuned for life. In an infinite multiverse, all possible values occur somewhere, and we necessarily find ourselves in one hospitable to observers. It's a selection effect, not a coincidence. Critics counter that this explanation is unfalsifiable and therefore unscientific. If anything we observe can be explained by saying, "That's the way it is in our bubble," the theory makes no testable predictions. Recent work searches for possible multiverse signatures, bubble collisions that might have left marks in the cosmic microwave background, or patterns in fundamental constants that might reveal their selection mechanism. The multiverse remains speculation, a possibility that challenges how we think about science, explanation, and the boundaries of knowledge. Let your consciousness split like a multiverse, each thought branching into its own dream bubble, separate and complete. Mystery 37. Cyclic universe models. Instead of beginning with the Big Bang, perhaps the universe undergoes infinite cycles of expansion and contraction. Each Big Bang would follow a big crunch, death and birth in eternal recurrence. Cyclic models face challenges. Entropy increases with each cycle, making the universe more disordered over time. If cycles have been occurring infinitely, the universe should be in maximum entropy, dark and dead. Yet it's not. Modern cyclic models attempt to address this by having each cycle larger than the last, diluting entropy. Or they propose that the bounce from contraction to expansion involves quantum effects that reset certain properties while preserving others. Some versions incorporate brains from string theory, with cycles driven by collisions between higher dimensional surfaces. Others use modified gravity theories that allow bounces instead of singularities. The cyclic picture has philosophical appeal: no beginning, no end, just eternal transformation. But it faces significant theoretical and observational challenges. Current evidence favors a universe with a definite beginning, though this conclusion could change with new discoveries. Your breathing cycles, in and out, each breath a little universe of its own. Neither the first nor the last, just another in an endless series. Mystery 38. Quantum fluctuations. As origin quantum mechanics tells us that vacuum fluctuations can create particle-antiparticle pairs that briefly exist before annihilating. Could a similar process have created the entire universe from quantum nothingness? Some theorists propose that the universe itself is a quantum fluctuation, an improbable but possible event given infinite time. If nothing is quantum mechanically unstable, universes might spontaneously nucleate from vacuum. This idea faces immediate challenges. How can time exist for fluctuations to occur if time itself was created by the fluctuation? What does nothing mean in quantum mechanics, where even vacuum has properties and structure? Alexander Vilenkin and others have developed models where the universe tunnels quantum mechanically from nothing into existence, described by a wave function that includes space-time itself. The universe wouldn't have a cause in the traditional sense, just a quantum probability. These ideas push against the boundaries of both physics and philosophy. Can something truly come from nothing? Does nothing even exist? Or must there always be quantum fields, laws of physics, mathematical structures? The question dissolves in the quantum foam of near sleep, where nothing and something blur together, where consciousness emerges from and returns to the unformed void. Mystery 39. The singularity at t equals 0. General relativity predicts that if we trace cosmic expansion backward, we reach a moment of infinite density and temperature, the initial singularity at time 0. But singularities are where physics breaks down, suggesting our theories are incomplete. Most physicists believe the singularity is unphysical, an artifact of applying general relativity beyond its domain of validity. When quantum effects are included, the singularity might be replaced by something else, a quantum state of minimal size, a bounce from a previous phase, or something we can't yet imagine. Loop. Quantum cosmology suggests the Big Bang was actually a bounce, with the universe contracting to a minimal size before expanding. String theory and other quantum gravity approaches offer similar possibilities for avoiding the singularity, but without a complete theory of quantum gravity, we can't definitively say what happened at time 0. The singularity marks the boundary of our knowledge, a reminder that our best theories have limits. Perhaps asking what happened at t equals 0 is like asking what's at the edge of the universe. The question might contain false assumptions, implying boundaries where none exist. Time dissolves for you now. There is no 0 hour, no singular moment of sleep's beginning, just a gradual fade from one state to another. Mystery 40. Why these physical constants? The fundamental constants of nature, the speed of light, the strength of gravity, the mass of the electron, determine what kind of universe we inhabit. But why do they have the specific values we observe? Change any constant significantly, and the universe becomes uninhabitable. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the electromagnetic force were different, atoms wouldn't form. If the strong nuclear force varied by a few percent, no complex nuclei could exist. This fine-tuning puzzle has several proposed solutions. The anthropic principle suggests we observe these values because universes with other values wouldn't produce observers. It's a selection effect. We're here because the constants allow us to be. The multiverse hypothesis proposes that all possible constant values exist in different universes, with ours being one of the rare habitable ones. Others seek a deeper theory that predicts these constants from first principles, removing the mystery. Perhaps the constants aren't truly constant, varying across space or time, or maybe they're linked in ways we don't yet understand, with apparent fine-tuning emerging from deeper relationships. Why you're you, with your particular thoughts and experiences, is similarly mysterious. Selection effects, chance, or something deeper. The question fades as you accept your own particular constants. Mystery 41. Gamma ray. Bursts. For a few seconds or minutes, a gamma ray burst outshines all other gamma ray sources in the observable universe. These are the most energetic explosions since the Big Bang, releasing in seconds as much energy as the sun will emit over its entire lifetime. Long-duration bursts, lasting more than 2 seconds, appear to come from the collapse of massive stars into black holes. Short-duration bursts seem to result from merging neutron stars or neutron-star black hole pairs, but mysteries remain about the exact mechanisms. How do these collapsing objects produce such focused beams of gamma rays? Why do the beams have the properties we observe? What happens in the first seconds of a black hole's birth to create such tremendous energy release? Some bursts show unexpected features: rapid variability, multi-component structure, ultra-high energy photons that challenge our understanding of physics. A few bursts don't fit either the long or short category, hinting at additional mechanisms we haven't identified. If a gamma-ray burst occurred in our galaxy, pointed toward Earth, it could threaten life through radiation damage to the atmosphere. Fortunately, they're rare and random in direction, making Earth's sterilization by burst unlikely, but not impossible. Let these explosive thoughts burst and fade, brilliant but brief, leaving only the afterglow of calm as you sink deeper into rest. Mystery 42. Fast radio. Bursts. Fast radio bursts are millisecond duration pulses of radio waves from deep space, each releasing as much energy as the sun emits in days. First discovered in 2007, they've puzzled astronomers ever since. Most fast radio bursts occur once and never repeat, making them nearly impossible to study. A few sources produce repeated bursts, allowing detailed follow-up observations. These repeaters helped astronomers identify host galaxies and measure distances, but deepen the mystery of what causes them. Proposed explanations include neutron-star collisions, magnetar eruptions, evaporating primordial black holes, pulsar companions, and even alien civilizations. Recent observations have narrowed the possibilities, with magnetars emerging as strong candidates, but questions remain. Why do some sources repeat while others don't? What determines burst properties? Why are there so many of them, thousands per day across the sky? And how can such compact sources produce such tremendous energy in such brief time? Each new burst brings new surprises, unexpected polarization, strange frequency structure, varied pulse shapes. The universe, it seems, has found yet another way to be brilliantly, briefly, inexplicably bright. Brief bursts of thought still flicker across your mind, growing fewer and fainter, each one fading like a fast radio burst into the cosmic background. Mystery 43. Magnetars. Take a neutron star, the collapsed core of a massive star, and give it a magnetic field 1,000 trillion times stronger than Earth's. You have a magnetar, one of the most extreme objects in the universe. Magnetars are so magnetic that atoms near their surface elongate into needle shapes. Their fields contain enough energy to heat their surfaces to millions of degrees, making them glow in X-rays. Occasionally, they experience starquakes, sudden fracturing of their solid crusts, which can trigger enormous energy releases. How do magnetars form such powerful magnetic fields? The leading theory involves dynamo processes during the supernova collapse that creates the neutron star, amplifying initial magnetic fields to extreme strengths. But details remain unclear. Magnetars produce unpredictable bursts and flares of X-rays and gamma rays. Some emit giant flares, briefly outshining all other X-ray sources in the galaxy. Others show persistent pulsations, dimming and brightening over months or years, for unknown reasons. A magnetar has been linked to at least one repeating, fast radio burst source, suggesting magnetars might explain these mysterious signals. But how a magnetar produces radio bursts remains unclear. If a magnetar existed within a few thousand light-years of Earth, its radiation could damage the ozone layer and threaten life. Fortunately, the nearest known magnetar is safely distant. Feel the pull of magnetic sleep, irresistible and strong, drawing you inward like metal to a magnetar. Mystery 44. Zombie stars. Some stars refuse to die properly. Type 1. X. Supernovae appear to be failed thermonuclear explosions where a white dwarf ignites but doesn't completely disrupt. The explosion is weaker than expected, and evidence suggests the white dwarf might survive, becoming what astronomers call a zombie star. These undead stars would be incredibly strange, partially disrupted white dwarfs, bloated and deformed, still shining but forever changed by their failed suicide attempt. They might look like ordinary stars but have peculiar compositions and behaviors. Zombie stars might also result from other processes. Some neutron stars might accrete matter from companions, gaining mass until they collapse into strange quark stars. Neutron stars transformed into a different exotic state. The transition might be visible as a peculiar transient event. Then there are stars that briefly die and resurrect. Luminous blue variables occasionally experience pseudo-supernovae, tremendous eruptions that could be mistaken for stellar death, but which the star survives, resuming normal fusion afterward. Whether these various zombies exist and how common they might be remains uncertain. The universe of stellar death is more complex than simple categories of supernovae types suggest. Your thoughts too might zombie walk briefly, half alive, neither fully conscious nor fully dreaming, before finally settling into peaceful sleep. Mystery. 45. Thorn-Zhitkov. Object: imagine a neutron star inside a giant star, a bizarre hybrid object proposed by Kip Thorne and Anna Zhitkov. This could form if a neutron star spirals into the core of a red giant or supergiant, replacing the normal stellar core with something far stranger. The neutron star core would be hot enough to drive fusion in the surrounding stellar envelope, creating a star that looks normal from outside but has a neutron star heart. Nuclear reactions near the neutron star surface would create unusual elemental abundances, providing observational signatures. Only one candidate Thorn-Zhitkov object has been identified, HV2112, in the Small Magellanic Cloud. It shows chemical peculiarities consistent with the theoretical predictions, but confirmation requires further observation. If these objects exist, they raise fascinating questions. How long do they survive? Does the neutron star eventually consume the envelope? What happens when the envelope is depleted? Could the system collapse into a black hole? The very possibility of such hybrid objects reminds us that stellar evolution, despite decades of study, still holds surprises. Stars can combine and merge in ways producing strange, almost impossible-seeming chimeras. Hybrid states of consciousness bridge waking and sleeping, your thoughts mixing and merging, neither purely one nor the other. Strange combinations that exist only in transition. Mystery 46. Blue stragglers. In ancient star clusters, where all stars should have evolved beyond the hot, blue main sequence phase, we find blue stragglers, stars that look young when they should be old. These stars didn't form recently. They've been rejuvenated. The leading explanation involves stellar collisions or mass transfer. In dense cluster cores, stars occasionally collide and merge, mixing fresh hydrogen into their cores and restarting vigorous fusion. Or a star might accrete mass from a companion, similarly rejuvenating itself. But mysteries persist. The exact mechanisms of stellar mergers remain unclear. How do two stars combine? What happens to their internal structure? Why do some blue stragglers show signs of rapid rotation while others don't? Some blue stragglers appear to have formed from triple star systems, with complex dynamics leading to collisions or mergers. Others might result from mass transfer in binary systems. There may be multiple pathways to blueness, each leaving different signatures. Blue stragglers also challenge our understanding of stellar populations. In globular clusters billions of years old, They represent recent events, adding a layer of youthful activity to ancient systems. Youth hidden in age, energy where it shouldn't be, unexpected activity in quiet places. Your sleeping mind might yet produce dream stragglers, vivid and energetic against the darkening background. Mystery 47. Hypervelocity stars. Some stars travel through the galaxy at tremendous speeds, over 1,000 kilometers per second, fast enough to escape the Milky Way's gravitational pull. These hypervelocity stars were likely ejected by encounters with the supermassive black hole at the galaxy's center. When a binary star system passes too close to a supermassive black hole, tidal forces can tear the pair apart. One star is captured by the black hole while its companion is flung outward at extreme velocity, carrying away the system's orbital energy. But some hypervelocity stars have trajectories inconsistent with galactic center ejection. Alternative mechanisms include supernova explosions in binary systems or dynamical interactions in dense star clusters. A few might even originate from dwarf galaxies disrupted by the Milky Way. These stellar exiles will eventually leave the galaxy entirely, wandering forever through intergalactic space. Any planets orbiting them would be carried along, becoming homeless worlds in the vast darkness between galaxies. Hypervelocity stars provide probes of extreme dynamics and tests of the galaxy's gravitational potential. Tracking them backward reveals their launch sites. Following them forward predicts their lonely trajectories. Stray thoughts accelerate through your mind, untethered and swift, some escaping into dreams, others fading into the intergalactic void of deep sleep. Mystery 48. Stellar streams. When the Milky Way's tidal forces rip apart dwarf galaxies and globular clusters, they leave behind stellar streams, rivers of stars flowing through the galaxy, marking the paths of their destroyed progenitors. These streams are fossils of galactic cannibalism, evidence of our galaxy's violent history of consuming smaller companions. By mapping stellar streams, astronomers reconstruct the Milky Way's assembly history and measure its dark matter distribution. But streams are fainter and more fragile than expected. They should persist for billions of years, yet many seem to be fading or disrupting faster than models predict. Unknown. Perturbing influences, perhaps dark matter, subalos, or molecular clouds, might be breaking them up. Some streams show gaps and clumps that challenge our understanding of tidal disruption. Others have chemical compositions, revealing multiple stellar populations in their progenitor systems, suggesting complex formation histories. The most spectacular stream, the Sagittarius stream, wraps entirely around the Milky Way, a ribbon of stars from a dwarf galaxy currently being devoured. Watching this cosmic feast unfold reveals both the dynamics of galaxy interactions and the three-dimensional structure of our galaxy's dark matter halo. Thoughts stream through your mind in tidal patterns, pulled and stretched by the gravity of sleep, fragmenting into disconnected clusters that eventually disperse. Mystery 49. The solar corona. Heating problem. The sun's visible surface temperature is about 6,000 degrees Celsius, yet the corona, the sun's outer atmosphere, reaches over 1 million degrees. How can the atmosphere be so much hotter than the surface below? This violates our everyday intuition that heat flows from hot to cold. Something must be continuously pumping energy into the corona, heating it to these extreme temperatures. But what? Proposed mechanisms include magnetic reconnection, where twisted magnetic field lines snap and release energy, and wave heating, where magnetic waves propagate outward from the surface, dissipating their energy as heat. Both probably contribute, but their relative importance remains debated. Recent high-resolution observations reveal the corona's fine structure, magnetic loops, jets, and rapidly evolving features. This complexity suggests heating occurs through many small events rather than a few large ones, a sort of magnetic nano-flare storm. Understanding coronal heating is crucial for predicting space weather, those eruptions of plasma that can damage satellites and power grids. It also applies to other stars, many of which have even more extreme coronae. The mystery persists despite decades of study and sophisticated observations. Nature refuses to reveal easily how it creates these million-degree atmospheres from mere thousands-degree surfaces. Heat fades from your skin now, your body cooling toward ambient temperature, energy dissipating into the surrounding air, approaching equilibrium as consciousness dims. Mystery 50, Betelgeuse's dimming. In late 2019 and early 2020, Betelgeuse, one of the brightest stars in the sky, dramatically dimmed to about 40% of its normal brightness. Was the red supergiant about to explode as a supernova? The dimming sparked worldwide interest and intense observation. Astronomers monitoring the star across multiple wavelengths found that part of Betelgeuse's surface had cooled, likely due to a massive stellar eruption that ejected gas and dust, temporarily obscuring the star. Betelgeuse returned to normal brightness, and the supernova alarm proved false, this time. But the event revealed how little we understand about massive star variability and mass loss. Red supergiants like Betelgeuse shed enormous amounts of material through stellar winds and eruptions, fundamentally changing before they explode. When will Betelgeuse actually explode? It could happen tomorrow or 100,000 years from now. We know it's in the late stages of stellar evolution, fusing heavy elements in its core, rapidly approaching the conditions for core collapse. But predicting the exact timing remains impossible. When Betelgeuse does explode, it will briefly outshine the moon in Earth's sky, a spectacular event visible even in daytime. But it's 600 light-years away. No threat, just a magnificent show. Your own light dims now, brightness fading, the spectacular show of waking consciousness approaching intermission, the performance of sleep ready to begin. Mystery 51, Planet 9. Something massive appears to be lurking in the outer solar system, its gravity shepherding distant objects into peculiar orbits. Dubbed Planet 9, this hypothetical world would be roughly 5 to 10 Earth masses, orbiting far beyond Neptune. Evidence comes from the clustered orbits of extreme trans-Neptunian objects. Their orbital orientations are suspiciously aligned, difficult to explain, without a massive perturber. Computer simulations show that a distant planet could produce exactly this pattern, but searches have found nothing despite years of effort. Planet 9, if it exists, would be extremely faint and moving slowly against the stars, making it exceptionally hard to find. It could lurk anywhere in a vast swath of sky. Alternative explanations include a disk of small objects providing the gravitational influence, or observational bias, making random orbital alignments appear significant. Some propose Planet 9 is actually a primordial black hole the size of a baseball, explaining why optical searches have failed. The mystery continues to drive both observation and theory. If Planet 9 exists, finding it would revolutionize our understanding of solar system formation. If it doesn't, we must explain the orbital clustering through other means. Something pulls at the edge of your consciousness, too distant to see clearly, influencing your thoughts' trajectories in subtle ways, present but unconfirmed. Mystery 52. Hot Jupiter migration. Gas giant planets like Jupiter should form beyond the snowline, where volatile ices condense. Yet we've discovered hundreds of Jupiter-mass planets orbiting closer to their stars than Mercury. Orbits our Sun, hot Jupiters, with surface temperatures exceeding 1,000 degrees. How did these giants migrate inward? Interaction with protoplanetary disks can cause orbital decay, with gas drag pulling young planets toward their stars. Gravitational interactions with other planets can also scatter orbits, sometimes sending planets inward. Once close to their stars, tidal forces circularize hot Jupiter's orbits, leaving them in their current tight configurations. But mysteries remain about the migration mechanism's details and relative importance. Why do only some systems have hot Jupiters? Our solar system kept its giant planets far from the Sun. What determines whether migration occurs? And how do hot Jupiters survive so close to their stars without being destroyed? Some hot Jupiters show signs of atmospheric escape, gradually evaporating under their star's intense radiation. Others exhibit unexpected chemical compositions, reflecting their migration histories. Each discovery adds complexity to our understanding. Migration happens in consciousness too, thoughts wandering from their origins, drifting towards strange attractors, settling into unexpected orbits around the gravity wells of sleep. Mystery 53. Super-Earth rarity in our solar system. Surveys of exoplanets reveal that the most common type of planet in the galaxy is the super-Earth. Worlds between Earth and Neptune in size, typically 1 to 4 times Earth's diameter, yet our solar system has none. Between Mars and Jupiter lies a gap where super-Earths might have formed. Why didn't they? One possibility is Jupiter. Its formation and migration might have scattered or ejected any super-Earths that tried to form in the inner solar system. Alternatively, conditions in our protoplanetary disk might have been unsuitable for super-Earth formation. Differences in disk mass, composition, or evolution could explain why our system's architecture differs from typical planetary systems. This raises a profound question. Is our solar system typical or unusual? Are we in a rare type of planetary system? And if so, does that rarity relate to Earth's habitability? Perhaps life-bearing worlds require unusual planetary architectures. Understanding why our system lacks super-Earths helps us understand planetary formation generally, and might reveal whether Earth-like worlds are common or rare in the galaxy. The answer has implications for the search for life beyond Earth. Your mental architecture is unique too, shaped by circumstances and chance, lacking some common features, possessing others in unusual configurations, special not by design but by contingency. Mystery 54. Exoplanet atmospheres. Detecting exoplanets was revolutionary, but characterizing their atmospheres is the next frontier. When a planet transits its star, starlight filters through the planet's atmosphere, carrying chemical signatures. We've detected water vapor, methane, carbon dioxide, and even exotic molecules like titanium, oxide in hot Jupiter atmospheres. But mysteries abound. Many hot Jupiters show fewer features than expected, possibly obscured by high-altitude clouds or hazes. Some planets have atmospheres escaping into space, stripped away by stellar radiation. Others show unexpected temperature structures, with daysides far hotter or cooler than models predict. The chemistry of exoplanet atmospheres often surprises us. For smaller Earth-like worlds, atmospheric characterization remains extremely challenging. Current technology barely detects the largest exoplanet atmospheres. Finding biosignature gases, oxygen, methane, phosphine, in Earth-sized planet atmospheres will require next-generation telescopes. But we're getting closer. Each new detection refines our techniques and understanding. Soon we might analyze the atmosphere of a potentially habitable world, searching for signs that we're not alone. Breathe deeply. Your atmosphere, too, is being analyzed by the autonomic systems of your body, oxygen and carbon dioxide measured and balanced, keeping you alive as you drift toward unconsciousness. Mystery 55. Habitable zone paradoxes. The habitable zone around a star, where liquid water can exist on a planet's surface, seems straightforward. Too close, water evaporates. Too far, water freezes. But reality is far more complex. Atmospheric composition dramatically affects habitability. A thick carbon dioxide atmosphere can warm a distant planet through greenhouse effects, expanding the habitable zone outward. Conversely, planets near the inner edge might lose their water through photodissociation and hydrogen escape. Tidal locking complicates matters for planets around red dwarfs. With one side always facing the star, would atmospheres freeze out on the dark side? Or would heat redistribute, making these worlds habitable despite their locked rotation? Subsurface oceans add another dimension. Moons like Europa and Enceladus are far outside the traditional habitable zone, yet host liquid water oceans beneath ice shells kept warm by tidal heating. How common are such hidden oceans? Then there's atmospheric loss. Mars was once wetter but lost most of its atmosphere. Venus, despite being in or near the habitable zone, underwent runaway greenhouse warming. Habitability isn't just about distance from a star, but about long-term stability and countless other factors. The zone of habitability in consciousness narrows as sleep approaches, a brief window where you're aware enough to notice but relaxed enough to let go. Mystery 56. Planetary magnetic fields. Earth's magnetic field protects us from solar wind and cosmic radiation, making complex life possible. But why some planets have strong magnetic fields, while others don't, remains partially mysterious. Earth's field comes from its liquid iron outer core, convecting and generating currents, a dynamo effect. Mars once had a magnetic field, but lost it when its core cooled and solidified. Venus, similar in size to Earth, has no significant field, possibly because its slow rotation prevents dynamo action. Among gas giants, Jupiter's magnetic field is enormous, generated by metallic hydrogen in its interior. Saturn's field is weaker, but still substantial. Uranus and Neptune have tilted, off-center fields that challenge our understanding of planetary dynamos. For exoplanets, we've barely begun to probe magnetic fields. Some hot Jupiters might have extremely strong fields, affecting their atmospheric structure and evolution. Others might lack fields entirely, changing how they interact with stellar winds. Magnetic fields also influence habitability. Without Earth's magnetic shield, solar wind would gradually strip away atmospheric gases. Mars's atmospheric loss accelerated after its field disappeared. For exoplanets around active stars, strong magnetic fields might be essential for retaining atmospheres. Your body's bioelectric field quiets as you approach sleep, neurons firing less frequently, the electromagnetic orchestra of consciousness diminishing to a gentle hum. Mystery 57. Formation of gas giants. Jupiter and Saturn are gas giants, composed mostly of hydrogen and helium, like the Sun. But how did they form? The standard model, core accretion, proposes that they began as rocky cores that grew large enough to gravitationally capture massive gas envelopes. But this model faces timing problems. Gas in protoplanetary disks disperses within a few million years. Can cores grow fast enough to capture gas before it disappears? For Jupiter-mass planets in wide orbits, the timescale seems too short. Alternative models propose direct gravitational collapse, with clumps in the protoplanetary disk fragmenting and collapsing directly into gas giants. This would work faster but requires specific disk conditions that might be rare. Recent discoveries of giant planets in wide orbits around young stars challenge both models. Some of these worlds are too far from their stars to have formed by core accretion, yet too massive to have formed by disk fragmentation. Perhaps both mechanisms operate under different conditions. Or maybe we're missing key physics about protoplanetary disk evolution, planet migration, or early solar system dynamics. The mystery of beginnings, how complexity emerges from simpler components, applies equally to planets and to consciousness, both arising through processes we incompletely understand. Mystery 58. Rogue planets. Not all planets orbit stars. Rogue planets, ejected from their birth systems or formed in isolation, drift through interstellar space in darkness and cold. How common are rogue planets? Estimates range wildly, from one per star to billions wandering the galaxy. Gravitational microlensing surveys have detected a few, but they're extremely difficult to find, cold, dark, and tiny against the vastness of space. Some rogues might have been ejected during violent early phases of planetary system formation, when gravitational interactions between young planets led to orbital chaos. Others might have formed in isolation in ways we don't yet understand. Could rogue planets be habitable? Surface life seems impossible without stellar warmth, but subsurface oceans heated by radioactive decay and tidal effects, if the planet has moons, might persist. Life could exist in eternal darkness, never knowing stars. Occasionally, a rogue planet might capture into a new star system, becoming a retrograde planet or getting scattered into an unusual orbit. Some of our solar system's odd objects might be captured rogues. Thoughts unmoored from waking logic drift like rogue planets through the interstellar space of near sleep, dark and cold, following trajectories determined by earlier ejections. Mystery 59. Ocean world liquid water exists far from Earth, beneath the ice of Jupiter's moon, Europa. In the subsurface ocean of Saturn's moon, Enceladus, possibly in Titan's depths and within Pluto's interior. Ocean worlds might be common in the outer solar system. These hidden oceans, warmed by tidal heating or radioactive decay, could be habitable despite never seeing sunlight. Europa's ocean might contain more water than all of Earth's oceans combined, with a seafloor in contact with rock that could provide chemical nutrients. We've detected water vapor plumes erupting from Enceladus and possibly Europa, offering tantalizing possibilities for sampling ocean material without drilling through kilometers of ice. Future missions might fly through these plumes, analyzing their chemistry for signs of life. But mysteries remain. How thick is the ice? How do nutrients cycle? Could energy sources support ecosystems? What exotic biochemistry might exist in these alien seas? Beyond our solar system, ocean worlds might be even more common. Many icy exomoons could harbor subsurface seas. The galaxy might be full of hidden oceans, life thriving in darkness beneath ice, never guessing at stars and galaxies above. Consciousness submerges now beneath the ice of waking thought, sinking into darker, quieter waters where different rules apply and strange forms swim. Mystery 60. Planetary Ring. Origin. Saturn's magnificent rings are iconic, but their origin remains mysterious. Are they ancient, dating to Saturn's formation? Or are they relatively young, formed by a shattered moon in the recent past? Evidence suggests youth. The rings are bright and clean, not darkened by micrometeorite bombardment as ancient rings would be. They might be only 100 million years old, less than 2% of Saturn's age. But if they're young, what created them? A moon wandering too close might have been ripped apart by tidal forces. Or perhaps a collision between moons shattered one into countless particles. The material then spread into the equatorial plane, forming the rings we see. Jupiter, Uranus, and Neptune also have rings, though far fainter than Saturn's. Each system has unique properties reflecting different formation mechanisms or evolutionary histories. Why doesn't Earth have rings? It might have in the distant past, if a large impact ejected debris. that temporarily formed a ring before falling back or escaping. Some theorize that the moon-forming impact created a temporary ring of debris. Rings are transient features, lasting only millions of years before dispersing or accreting into moons. We're fortunate to live when Saturn's spectacular rings exist for our wonder. Rings of thought circle and circle, temporary patterns that will disperse by morning, leaving no trace except perhaps a memory of their beauty. Mystery 61, the Arrow of Time. Time flows in one direction, from past to future, from order to disorder, from cause to effect. But the fundamental laws of physics are time-symmetric. They work equally well forward or backward. So why does time have an arrow? The answer involves entropy, the measure of disorder. The second law of thermodynamics states that entropy always increases. Broken eggs don't reassemble. Mixed coffee and cream don't separate. Heat flows from hot to cold, never the reverse. But this just rephrases the mystery. Why does entropy increase? Because the universe started in a low entropy state, the Big Bang was extremely ordered. As the universe evolves, it explores more and more of the available state space, increasing entropy. Yet this explanation raises new questions. Why was the Big Bang's entropy so low? It seems like a highly improbable initial condition requiring explanation. Some cosmologists propose that the pre-Big Bang state or multiverse context explains it. The psychological arrow of time, our sense of past and future, memory and anticipation, might emerge from the thermodynamic arrow. Our brains are entropy-increasing systems, and memory formation is an irreversible process. Time's arrow carries you forward into sleep, irreversibly, memories of the day forming and consolidating, tomorrow awaiting your arrival. Mystery 62. Time dilation extremes. Near a black hole's event horizon, time slows dramatically relative to distant observers. If you watched a friend fall into a black hole, you'd see them freeze at the horizon, their time dilating infinitely from your perspective. But what would they experience? They'd fall through smoothly, noticing nothing special at the horizon itself. The entire external universe would speed up in their frame, and they might watch stars age and die as they fell inward. The most extreme time dilation occurs at black hole event horizons, but intense gravitational fields elsewhere also produce significant effects. On neutron star surfaces, time runs measurably slower than on Earth. GPS satellites experience tiny time dilation effects that must be corrected. Velocity also dilates time. At near light speeds, years could pass on Earth while only days pass for the traveler. The famous twin paradox, not actually a paradox, but a real consequence of special relativity. Could extreme time dilation be used for time travel? Theoretically, yes, to the future. Orbit close to a black hole, return home, and find Earth aged by centuries. But no known mechanism allows travel to the past. Your perception of time already distorts. Hours of sleep will seem like minutes. The night will pass in subjective moments, time compressed by consciousness's absence. Mystery 63. Closed time-like curves. Einstein's equations permit solutions containing closed time-like curves, paths through space-time that loop back on themselves, allowing travel to one's own past. These exist mathematically, but do they exist physically? The Gödel universe, a solution found by Einstein's friend Kurt Gödel, contains closed time-like curves. So does the interior of a rotating black hole and the space near certain wormhole configurations. But these solutions might be unphysical, forbidden by quantum effects or causality protection mechanisms. Closed time-like curves create logical paradoxes. If you traveled back and prevented your own birth, what happens? Physics might resolve this through the Novikov self-consistency principle, Only self-consistent histories are possible. You can't prevent your birth because you didn't. Or perhaps quantum mechanics allows multiple histories with closed time-like curves creating branching timelines. You could travel back and change the past, but you'd enter a different quantum branch, not your original timeline. Most physicists suspect that nature forbids closed time-like curves through some mechanism we don't yet understand, perhaps quantum gravity effects that prevent their formation. The universe protects causality by forbidding paradoxes. Thoughts can loop back on themselves in dreams, time becoming circular, cause and effect blurring together in closed curves of surreal logic. Mystery 64, Space-Time Fabric Nature. We visualize space-time as a fabric that mass and energy curve, creating gravity. But what is this fabric actually made of? Is space-time fundamental or emergent? At the Planck scale, 10 to the power of -35 meters, quantum effects should dominate, and space-time might become grainy or discrete rather than smooth and continuous. Some theories propose space-time emerges from more fundamental entities. Loop quantum gravity suggests space-time has a granular structure, woven from quantum loops of gravitational field. String theory proposes that space-time emerges from the dynamics of vibrating strings. Other approaches suggest space-time might be holographic, emergent from information encoded on boundaries. If space-time is emergent, what is it emerging from? And why does it appear continuous at accessible scales? These questions probe the deepest foundations of reality, asking what the universe is made of at the most fundamental level. The nature of space-time connects to the measurement problem in quantum mechanics, the origin of physical laws, and the relationship between information and reality. Understanding space-time's true nature might require a complete theory of quantum gravity. The fabric of your awareness thins now, becoming less substantial, perhaps revealing that consciousness, too, emerges from simpler components, reducible to neurons and chemistry, or perhaps irreducibly strange. Mystery 65, Extra Dimensions. String theory requires extra spatial dimensions beyond the three we experience. Where are these dimensions? The leading proposal is that they're compactified, curled up so small we can't detect them. Imagine a garden hose. From far away it looks one-dimensional, a lice. But an ant walking on it discovers a second dimension curled into a tiny circle around the hose. Extra dimensions might be similarly hidden, too small to perceive directly. Different compactification schemes produce different physics in our observable three dimensions, potentially explaining why fundamental particles have their observed properties. The shape and size of extra dimensions could determine the constants of nature. Could extra dimensions be detected? If they're large enough, gravity might leak into them at short distances, weakening more rapidly than expected. Particle colliders might create particles that travel through extra dimensions. Black holes might reveal extra-dimensional effects. Alternatively, extra dimensions might not exist at all. String theory might be wrong, or other formulations might eliminate the need for hidden dimensions. The question remains open, awaiting experimental resolution. Your consciousness doesn't require extra dimensions, yet dreams sometimes feel multi-dimensional. Spaces within spaces, impossible geometries unfolding in mental landscapes unconstrained by physics. Mystery 66, Quantum Foam. At the Planck scale, quantum fluctuations should become so intense that space-time itself fluctuates wildly, boiling with virtual black holes and wormholes constantly forming and dissolving. A quantum foam underlying reality. This foam would be utterly imperceptible at everyday scales, smoothing out to the continuous space-time we experience. But it has profound implications. Perhaps particles are topological defects in this foam. Maybe the vacuum energy driving cosmic acceleration originates here. Quantum foam suggests that at the smallest scales, space and time lose their ordinary meaning. There's no smooth geometry, no definite metric, just a probabilistic froth of possibilities. The familiar space-time of general relativity emerges only statistically. Testing these ideas is extraordinarily difficult. The Planck length is 10 to the power of 20 times smaller than an atomic nucleus. No conceivable experiment can probe such tiny scales directly. Indirect tests through astronomical observations or quantum gravity effects might offer the only hope. Some theories suggest quantum foam isn't just mathematical speculation, but has observable consequences, limiting the precision of measurements, affecting the propagation of light, or contributing to the cosmological constant. Thoughts dissolve into foam at sleep's edge, coherence breaking down into random fluctuations, structure giving way to quantum randomness of neuronal firing. Mystery 67. Wormhole possibility. General relativity permits wormholes, shortcuts through space-time connecting distant regions or even different universes. Enter one mouth, exit the other, having traveled through a tunnel in space-time rather than through ordinary space. But traversable wormholes require exotic matter with negative energy density to hold them open. Quantum field theory permits negative energy densities in limited contexts, but whether enough exotic matter exists to stabilize a wormhole remains unknown. Even if naturally stable wormholes are impossible, advanced civilizations might construct them using exotic matter or through manipulation of quantum fields. This remains speculation, but the physics doesn't absolutely forbid it. Wormholes connected to black holes might exist, but be untraversable, offering no practical shortcut. Or they might connect only to other universes in the multiverse, unreachable from our space-time. If wormholes could be created and controlled, they might enable time travel, creating closed time-like curves with all their attendant paradoxes. This might be why nature forbids them, to protect causality. Passages through consciousness open and close, shortcuts from one thought to another, associations tunneling through mental space, connections that bypass ordinary logic. Mystery 68. Causality violations. Can effects precede causes? Quantum mechanics shows correlations that seem to violate our intuitive understanding of causality. Entangled particles affect each other instantaneously, apparently faster than light, but these quantum correlations can't transmit information, preserving causality at the operational level. You can't use entanglement to send messages backward in time or faster than light. Nature seems to protect causality even while permitting strange correlations. Other potential causality violations include tachyons, hypothetical faster-than-light particles that move backward in time. If they exist, they create logical paradoxes. Most physicists believe tachyons are unphysical, forbidden by the requirement of causality. Advanced solutions to Einstein's equations, like closed time-like curves and certain wormhole configurations, permit causality violations in principle. Whether nature actually allows these solutions to be realized remains unknown. Perhaps quantum gravity enforces a chronology protection principle, preventing causality violations through mechanisms we don't yet understand. Or maybe the multiverse allows causality-violating events by branching timelines. Causality dissolves in dreams, where effects precede causes, where impossible sequences feel natural, where time loses its arrow and events connect by association rather than logic. Mystery 69. Frame dragging. Rotating mass drags space-time itself into rotation, a phenomenon called frame dragging or the lens Thirring effect. Near rotating black holes, space-time swirls like water circling a drain, forcing everything to orbit in the same direction. Earth's rotation drags space-time too, though the effect is tiny, detected only through precise measurements of satellite orbits. Rotating neutron stars drag frames more dramatically, affecting the orbits of companion stars or accretion disks. Near a maximally rotating black hole's ergosphere, a region outside the event horizon, frame dragging becomes so extreme that nothing can remain stationary. Even light beams are dragged around, unable to hold position. Frame dragging could theoretically be used to extract energy from rotating black holes. Through the Penrose process, matter dropped into the ergosphere can emerge with more energy than it entered with, stealing rotational energy from the black hole. This bizarre consequence of general relativity shows that space-time isn't a passive stage but an active participant in cosmic dynamics, twisted and dragged by mass and rotation. Your frame of reference shifts as you rotate through states of consciousness, perspective dragging through the ergosphere of sleep, unable to maintain waking awareness's fixed viewpoint. Mystery 70. Gravitational time dilation limits. The closer you get to a black hole's event horizon, the more extreme time dilation becomes, approaching infinity at the horizon itself. But what about beyond? Inside the horizon, do the equations remain meaningful? At the singularity, time dilation becomes undefined, another sign that general relativity breaks down there. Quantum gravity should take over, but we don't have a complete theory to describe what happens. For neutron stars, time dilation is extreme but finite. A clock on a neutron star surface runs about 30% slower than one far from gravitational fields. This measurably affects neutron star physics and must be accounted for when interpreting observations. The most extreme time dilation might occur in exotic scenarios. Inside rotating black holes, near cosmic strings, or in the early universe during certain phase transitions. Each case pushes general relativity to its limits. Could organisms evolve to exploit time dilation? A civilization orbiting close to a black hole could watch the outside universe age rapidly, waiting for conditions to improve elsewhere. But they'd experience less time themselves, a kind of temporal refuge. Time dilates toward infinity as consciousness approaches sleep's event horizon. The external world accelerates away, night passing swiftly, while you experience timeless suspension. Mystery 71. Quantum entanglement at cosmic scale. When particles become entangled, they share a quantum state. Measure one, and you instantly know something about the other, regardless of distance. But how far can entanglement extend? Experiments have demonstrated entanglement over hundreds of kilometers using satellite links. Theoretically, it should extend to cosmological distances. Photons from opposite sides of the universe could be entangled if they interacted in the early universe. The cosmic microwave background might contain entangled photons, carrying correlations from the Big Bang's first moments. If we could measure these entanglements, we might learn about quantum processes in the early universe, but practical challenges are enormous. Maintaining entanglement over cosmic distances while isolating quantum states from decoherence approaches impossibility. Still, the theoretical possibility exists, connecting quantum mechanics to cosmology in fascinating ways. Some theories suggest that space-time itself emerges from quantum entanglement patterns, that the smooth geometry of general relativity is actually a large-scale manifestation of microscopic entanglements. Space would be quantum correlation made manifest. Your thoughts entangle with fading sensory input, correlations spanning the distance between waking and sleeping, connected yet separating, information flowing between states. Mystery 72. Wave function collapse universe-wide. In quantum mechanics, particles exist in superposition until measured, when the wave function collapses to a definite state. But when exactly does collapse occur? And does it happen instantly throughout the universe? The measurement problem, understanding what constitutes a measurement and why it causes collapse, remains unsolved after a century of quantum mechanics. Different interpretations handle it differently. The Copenhagen interpretation says collapse occurs upon measurement but doesn't specify what qualifies as a measurement. The many worlds interpretation eliminates collapse, saying all possibilities occur in different branches. Objective collapse theories propose physical mechanisms for collapse. If collapse is real and instantaneous, it seems to violate relativity's prohibition on faster-than-light influence. But since collapse is random, it can't transmit information, preserving causality while challenging our understanding of non-locality. At cosmic scales, does the universe's wave function collapse? If so, who or what measures it? Or does it remain in superposition? All possible universal histories coexisting. These questions merge quantum mechanics with cosmology. Your consciousness collapses from the superposition of possible thought states into the definite state of sleep, observation by awareness ceasing, allowing the wave function to evolve unopposed. Mystery 73. The measurement problem. Why does observation change quantum systems? Before measurement, a particle can be in multiple states simultaneously. After measurement, it's in one definite state. What happened? The standard interpretation avoids answering directly, treating measurement as a primitive concept outside the theory's scope. But this leaves a conceptual gap. Measurement apparatuses are made of quantum particles too. Why do they cause collapse? Decoherence theory shows how interactions with the environment suppress quantum interference, making superpositions appear to collapse into classical mixtures. This explains much but doesn't fully solve the measurement problem. It describes how the appearance of collapse emerges but doesn't explain whether true collapse occurs. Some theories propose that consciousness causes collapse, making observers fundamental to reality. Others suggest gravity causes collapse when mass distribution becomes sufficiently ambiguous. Still others deny collapse happens at all, embracing many worlds or hidden variables. The measurement problem might be physics' most profound mystery, questioning the boundary between quantum and classical, the role of observation in reality, and whether the universe exists independently of measurement. You cease to measure the world as sleep arrives, observation ending, the classical definiteness of waking thought giving way to the quantum superposition of dream logic. Mystery 74, Schrödinger's cat cosmology. Schrödinger's famous thought experiment puts a cat in superposition, both alive and dead until observed. Applied to the universe, this creates profound puzzles. The universe contains no external observer. So if observation causes wave function collapse, who collapses the universe's wave function? Is the universe in superposition of all possible states? Does it require observers within it to create definite reality? The many worlds interpretation says yes, the universe is in superposition, with every quantum possibility realized in different branches. Our perception of a single definite universe is parochial, reflecting our position in one branch. Other interpretations handle cosmic measurement differently. Decoherence explains how definite classical reality emerges from quantum substrate without invoking observation. Objective collapse theories propose that large systems spontaneously collapse without observers. These questions about cosmic quantum mechanics connect to cosmology's initial conditions. Was the Big Bang in a definite state or a quantum superposition? How do we apply quantum mechanics to the universe as a whole when standard quantum mechanics assumes an external classical world? The universe's wave function might include all possible configurations, all possible histories, all possible yous, each dreaming different dreams in different branches. Mystery 75. Quantum tunneling in stars. Stars shine through nuclear fusion, but there's a problem. Nuclei are positively charged and repel each other. At the temperatures and pressures in stellar cores, They shouldn't have enough energy to overcome this electric repulsion and fuse. Yet they do through quantum tunneling. Quantum mechanics allows particles to occasionally appear on the other side of energy barriers they classically couldn't cross. In stars, nuclei tunnel through the Coulomb barrier, enabling fusion at lower energies than classical physics would require. Without quantum tunneling, stars would require much higher core temperatures to fuse hydrogen. The sun might never have ignited, or stars might live drastically different lifetimes. Quantum mechanics at the smallest scales determine stellar evolution at the largest scales. This illustrates quantum mechanics' cosmic importance. The very small doesn't stay small. Quantum effects scale up through fusion, nuclear energy generation, stellar evolution, and ultimately the chemical enrichment of the universe. Every atom heavier than hydrogen and helium was forged through quantum tunneling in stars or supernovae. You're made of quantum-tunneled nuclei, your existence depending on microscopic violations of classical energy barriers. Consciousness tunnels through barriers too, occasionally penetrating into sleep without permission, microsleep events intruding into waking, quantum leakage between states. Mystery 76, zero-point energy. Even at absolute zero temperature, quantum systems retain energy, zero-point energy, arising from Heisenberg's uncertainty principle. The vacuum itself seethes with this irreducible quantum energy. Calculating vacuum energy from quantum field theory gives an absurdly large value, so large it should have torn the universe apart immediately. Yet we observe a cosmological constant vastly smaller. This is the vacuum catastrophe, one of physics' greatest unsolved problems. Zero-point energy produces observable effects. The Casimir effect, where parallel metal plates experience attractive force in vacuum, arises from zero-point fluctuations. Virtual particles briefly borrowing zero-point energy enable processes like Hawking radiation. Could zero-point energy be harvested? Despite claims in science fiction and fringe physics, extracting energy from vacuum appears impossible. It would violate energy conservation and thermodynamics. The vacuum is the lowest energy state by definition. Some cosmologists propose that dark energy is vacuum energy, though reconciling the calculated and observed values remains a monumental challenge. Others suggest multiple vacuum states, with our universe trapped in a false vacuum that could eventually decay. Energy remains in your neurons even at rest, zero-point activity maintaining minimal function, the quantum substrate of consciousness persisting even as awareness fades. Mystery 77. Virtual particles. Quantum mechanics allows particle-antiparticle pairs to spontaneously appear from vacuum, exist briefly, then annihilate. These virtual particles aren't directly observable, but produce measurable effects. Virtual particles contribute to atomic energy levels through the Lamb shift, verified by precision spectroscopy. They create the Casimir force between conducting surfaces. Near black hole horizons, they generate Hawking radiation when separated across the event horizon. But what are virtual particles really? They're mathematical tools in quantum field theory calculations, representing intermediate states in Feynman diagrams. Whether they exist in any meaningful sense remains debatable. Some physicists argue virtual particles are just convenient fictions for describing quantum field vacuum fluctuations. Others treat them as ephemeral but real, constantly appearing and disappearing throughout space. Virtual particles blur the line between existence and non-existence. They exist long enough to affect reality, but briefly enough to violate energy conservation temporarily, permitted by Heisenberg's uncertainty principle. Thoughts at sleep's edge are like virtual particles, appearing briefly, barely real, violating the conservation laws of logical consistency, permitted only by consciousness's uncertainty. Mystery 78, Casimir Effect, Cosmic Implications. Two metal plates in vacuum experience attractive force, the Casimir Effect, arising because certain vacuum fluctuations are excluded between the plates, while all fluctuations exist outside, creating pressure imbalance. This tiny effect, measured in laboratories, demonstrates that vacuum isn't empty, but filled with quantum fluctuations. But what are the cosmic implications? Some theories propose that the Casimir effect influenced structure formation in the early universe. Quantum fluctuations might have been suppressed at certain scales, affecting the pattern of galaxy formation we observe. Could the Casimir effect contribute to dark energy? Probably not directly. The energy scales are vastly different. But it demonstrates that vacuum energy is real and physical, lending credence to vacuum energy as dark energy source. Exotic applications involve using Casimir forces to stabilize wormholes or manipulate vacuum energy. These remain speculative, requiring technology far beyond current capabilities. The Casimir effect reminds us that empty space isn't empty, but structured by quantum fields, with potential energy gradients and excluded states shaping reality in subtle ways. Space between thoughts empties as sleep approaches, yet isn't truly empty, still structured by the quantum substrate of neuronal activity, the Casimir force of consciousness pressing thoughts together. Mystery 79, Quantum Decoherence. Quantum systems interact with their environment, becoming entangled with countless surrounding particles. This decoherence process destroys quantum superposition, making systems behave classically. Decoherence explains why we don't observe macroscopic superpositions. Schrödinger's cat rapidly decoheres through interaction with air molecules, light, and its own thermal radiation, becoming definitely alive or dead rather than quantum superposed. But decoherence doesn't solve the measurement problem completely. It explains why superpositions appear to collapse, but not whether they actually do. In many worlds' interpretation, decoherence creates separate branches without collapsing the global wave function. At cosmic scales, what decoheres the universe? Perhaps nothing. The universe as a whole might remain in superposition. Or perhaps cosmic expansion, gravitational effects, or interactions with a wider multiverse provide decoherence. Understanding decoherence is crucial for quantum computing, where maintaining quantum coherence determines computational power. It's also essential for quantum biology, where quantum effects might play roles in photosynthesis, bird navigation, or even consciousness. Your sensory coherence with the environment decreases as sleep approaches, entanglement with the external world dissolving, leaving you isolated in subjective quantum state. Mystery 80, EPR paradox at cosmic scale. Einstein, Podolsky, and Rosen proposed a paradox. Quantum mechanics allows instantaneous correlations between distant particles, seemingly violating locality. Einstein called this spooky action at a distance. Experiments have confirmed that entangled particles do show such correlations, choosing complementary states instantaneously regardless of separation. But no information travels faster than light, preserving causality while demonstrating quantum non-locality. At cosmic scales, this non-locality could connect distant regions. Photons from opposite cosmic horizons might be entangled through interactions in the early universe, creating correlations spanning distances. Light hasn't had time to cross since the Big Bang. Some theories propose that space-time itself emerges from quantum entanglement patterns, that Einstein's spooky action actually underlies the geometric structure of general relativity. Space would be quantum correlation made manifest. The EPR paradox challenges our intuition about separated systems being independent. Even across cosmic distances, quantum systems can form holistic wholes. their properties correlated in ways that defy classical explanation. Your separated thoughts correlate strangely as sleep approaches, distant mental events influencing each other through the quantum entanglement of neural networks, consciousness's non-local connections. Mystery 81, the Fermi Paradox. If intelligent life is common in the universe, where is everybody? This is the Fermi Paradox. The galaxy is billions of years old and contains billions of stars. Even slow interstellar travel could colonize it in mere millions of years. Why don't we see evidence of alien civilizations? Proposed solutions include: life is rare, intelligence is rare, technological civilizations destroy themselves, they're hiding, they're already here, but undetected. We're first. They're incomprehensibly advanced and beyond our detection. Or interstellar travel is impractically difficult. Each solution has problems. If life is common, why the silence? If it's rare, why? What barrier prevents its emergence? The paradox grows more pressing as we discover countless exoplanets, many potentially habitable. Recent suggestions include that civilizations inevitably develop technologies that destroy them, or that advanced civilizations recognize interstellar communication as dangerous and maintain silence, or perhaps intelligence simply isn't selected for long-term survival. The paradox might resolve through the anthropic principle. We're having this conversation in a time and place where we can, which might be rare, or through the zoo hypothesis. They know we're here and are watching without interfering. Or perhaps the galaxy teems with simple life, microbes and vegetation, but complex cognition is astronomically rare, emerging only once in billions of planets. We might be alone, not because life is rare, but because brains are. The silence might be the universe's most profound message, telling us something important about the nature of life, intelligence, or cosmic destiny. Listen to the silence now, the quiet that surrounds your thoughts, as vast and significant as the space between stars. Mystery 82, Drake Equation Uncertainties. The Drake equation attempts to estimate the number of communicative civilizations in our galaxy by multiplying factors: star formation rate, fraction with planets, planets per star in habitable zones, fraction developing life, fraction developing intelligence, fraction developing technology and civilization lifetime. We know the first few factors reasonably well. Our galaxy forms several stars per year. Most have planets, and habitable zone planets appear common, but the biological and sociological factors remain completely uncertain. What fraction of habitable planets develop life? We have a sample size of 1. Does life emerge readily from chemistry, or did Earth require extraordinary luck? The answer changes the equation by orders of magnitude. Similarly, what fraction of life-bearing worlds develop intelligence? Earth had life for billions of years before brains appeared. Is intelligence inevitable given enough time, or does it require rare circumstances? The most uncertain factor is civilization lifetime. How long do technological civilizations survive? Decades, millennia, millions of years? Our own survival is uncertain, making predictions about others hazardous. Depending on assumptions, the Drake equation predicts anywhere from 0 to millions of communicative civilizations in our galaxy. This uncertainty reflects our fundamental ignorance about life's prevalence and intelligence's rarity. Equations attempting to quantify consciousness face similar uncertainties. What generates awareness? How common is it? How long does it persist? Your own consciousness, too, is a Drake equation of Vastness. Mystery 83, Panspermia. Did life originate on Earth, or did it arrive from elsewhere? Panspermia proposes that life, or its precursors, might travel between worlds on meteorites or comets, seeding planets throughout the galaxy. We know rocks are ejected from planets by large impacts and that some microorganisms can survive in space. Martian meteorites reach Earth regularly. Could life travel similarly? The challenges are formidable. Space radiation and cosmic rays damage DNA. Journey times between stars span millions of years. An arrival on a new planet must occur gently enough to preserve living cargo. But extremophile bacteria show remarkable resilience. Spores can survive extreme conditions for extended periods. And if protected inside large rocks, microbes might endure interstellar journeys. Directed panspermia, intelligent seeding of planets with life, sidesteps some problems. An advanced civilization might deliberately spread life, choosing targets and protection methods. We might be the result of ancient cosmic gardening. If panspermia occurs, life might be more widespread than independent origins would suggest, but it just pushes the question back. Where did the original life originate? The mystery of life's origin remains, merely relocated. Seeds of dreams drift through your mind, landing in the fertile soil of neural networks, germinating into strange growths that will bloom when REM sleep arrives. Mystery 84. Origin of Life, Chemistry. How did non-living chemistry become living biology? This is abiogenesis, one of science's greatest unsolved problems. We don't know how life began on Earth, much less whether it's common elsewhere. The Miller-Urey experiment showed that organic molecules form readily from simple chemistry and energy, but getting from amino acids to self-replicating systems requires many steps we don't understand. The RNA world hypothesis proposes that RNA, capable of both storing information and catalyzing reactions, preceded DNA protein life. But how did the first RNA molecules form and begin evolving? The transition from chemistry to biology remains murky. Other theories invoke clay minerals as templates, deep-sea hydrothermal vents as energy sources, or metabolic cycles preceding genetics. Each faces challenges explaining how simple chemicals organized into the complex, self-maintaining systems we call life. Some suggest life's origin required such improbable circumstances that it happened only once in our galaxy, making us alone. Others argue that given the right conditions, life emerges readily and inevitably. Until we find life elsewhere or create it from scratch in laboratories, the question remains open. The spark that animated the first living cell remains mysterious, hidden in deep time. Chemistry becomes biology at consciousness's edge, as you transition from waking metabolism to sleep's different biochemical state, animated matter following its programming toward rest. Mystery 85. Biosignature detection. How would we recognize alien life? Oxygen in an exoplanet atmosphere might indicate photosynthesis, but could also come from water photolysis. Methane suggests biology, but also geological processes. Finding unambiguous biosignatures is harder than it seems. We're searching primarily for life like ours, carbon-based, water-dependent, using similar biochemistry. But alien life might be radically different. Silicon-based life, ammonia solvent biochemistry, or something completely unimagined might leave signatures we wouldn't recognize. Even detecting Earth-like life from light years away presents enormous challenges. Current telescopes can barely characterize super-Earth atmospheres. Detecting biosignatures on true Earth analogs requires next-generation space telescopes. The search for technosignatures, evidence of technology, offers another approach. Radio signals, laser pulses, atmospheric pollution, Dyson spheres, or megastructures might be easier to detect than biosignatures, though they'd indicate rarer, more advanced civilizations. We might already have observed biosignatures without recognizing them. Novel signatures of exotic biochemistry could be in our data, awaiting interpretation. Or life might be obvious once we know where and how to look. The universe might be writing its signature across your thoughts now, patterns of neural activity that will someday be recognized as consciousness's unmistakable mark. Mystery 86, Technosignatures. Beyond biosignatures, we search for technosignatures, evidence of alien technology. Radio telescopes scan for artificial signals. Optical telescopes search for laser pulses. We look for megastructures, atmospheric pollution, waste heat, anything suggesting advanced civilization. The search for extraterrestrial intelligence, SETI, has monitored billions of radio channels from millions of stars. So far, silence. Except for a few unexplained signals like the WOW signal, never repeated or confirmed. Perhaps we're looking wrong. Advanced civilizations might communicate using neutrinos, gravitational waves, or methods we haven't imagined. Our radio searches might be like using smoke signals to detect fiber optic networks. Or perhaps civilizations are common but short-lived. Nuclear war, climate catastrophe, artificial intelligence gone wrong, nanotechnology accidents. Technological species might invariably destroy themselves shortly after developing radio capability. The absence of evidence might itself be evidence. Evidence that intelligence is rare, that interstellar communication is impractical, that civilizations hide, or that we're first. Each possibility has profound implications. Searching for technosignatures, we're also searching for hope. Proof that intelligence can survive its technological adolescence, that our cosmic loneliness might end, that the universe contains kindred minds. Your own technosignatures fade, the phone forgotten, the computer sleeping, technology receding as biological rhythms reassert themselves, preparing for the ancient technology of sleep. Mystery 87, The Great Filter Hypothesis. If life is common but we see no evidence of it, perhaps something prevents civilizations from becoming spacefaring and visible. This barrier is called the Great Filter. The filter could be behind us. Perhaps abiogenesis is extraordinarily rare, or the jump to multicellularity is nearly impossible, or intelligence seldom evolves. If so, we've passed the filter and the galaxy awaits our exploration. Or the filter lies ahead. Perhaps civilizations inevitably destroy themselves with nuclear weapons, climate change, bioengineered plagues, or artificial intelligence. We're approaching the filter, our survival uncertain. A filter ahead is more terrifying. It suggests that no matter how careful we are, some disaster awaits, unknown and unavoidable. Perhaps civilizations reach certain technological levels and invariably collapse. Finding simple life elsewhere would be bad news for the Great Filter hypothesis. It would suggest life's origin isn't the barrier, meaning the filter likely lies ahead in our future, a disturbing prospect. The silence of the cosmos might be the Great Filter's evidence, the cemetery of civilizations that didn't make it. We navigate uncertainly toward our own encounter with whatever stopped the others. Filters in consciousness prevent full waking awareness from persisting into sleep. These filters are benign, protective, ensuring rest. But they're filters nonetheless, barriers consciousness cannot cross. Mystery 88, Intelligence Evolution. Why did intelligence evolve on Earth? What selective pressures favor brains? Brains are metabolically expensive, requiring tremendous energy. What benefits justified this cost? Tool use, social cooperation, environmental unpredictability. Various factors might select for intelligence. But why did humans develop far beyond what survival requires? We write poetry, prove theorems, compose symphonies. How did natural selection produce this? Perhaps intelligence resulted from runaway sexual selection, like peacock tails. Smart mates were preferred, creating feedback loops toward greater intelligence regardless of survival utility. Or maybe intelligence is a spandrel, an accidental byproduct of selection for other traits. Brain size increased for various reasons, and consciousness and abstract thought emerged as side effects. The rarity of human-level intelligence, appearing only once in Earth's 4 billion-year biological history, suggests it's not inevitable or necessarily advantageous. Bacteria, evolutionarily speaking, are far more successful than humans. If intelligence is rare even on life-bearing planets, the galaxy might teem with microbes and vegetation while remaining devoid of minds. We might be the only consciousness for thousands of light years. Your intelligence dims now, selected against by circadian rhythms that favor periodic unconsciousness. Evolution built these sleep cycles as firmly as it built your waking mind. Mystery 89. Consciousness in the Cosmos. What is consciousness? How does subjective experience arise from physical processes? Is consciousness unique to Earth, or does it pervade the cosmos? The hard problem of consciousness, explaining why physical processes feel like something, remains unsolved. We can map brain activity, identify neural correlates of consciousness, but can't explain the emergence of qualia, of subjective experience. Panpsychism proposes that consciousness is fundamental, that all matter has some degree of experience. Human consciousness would be extremely complex consciousness, while electrons might have infinitesimal awareness. This solves the emergence problem by denying it. Others argue consciousness emerges from information processing, from integrated information, or from quantum processes in microtubules. Each theory faces challenges explaining the transition from unconscious matter to conscious experience. Could silicon-based computers become conscious? Could alien minds be so different from ours that we wouldn't recognize them as conscious? Might the universe itself be conscious in some sense? We don't know if consciousness is common or rare in the cosmos. Earth might be the only place where matter has arranged itself to experience existence, or consciousness might be universal, inherent in reality's fabric. Your consciousness fades into the cosmic background now, joining whatever universal field of awareness might exist, or dissolving into pure mechanism, chemistry without experience. Mystery 90. The Anthropic Principle. Why is the universe suitable for life? The fundamental constants seem fine-tuned for our existence. Change them slightly, and no stars, atoms, or life could exist. The weak anthropic principle notes that we observe a life-supporting universe because we couldn't exist in any other kind. It's a selection effect. Lifeless universes go unobserved. The strong anthropic principle suggests the universe must have properties allowing consciousness to develop. This raises questions about teleology and purpose in physics. These principles are controversial. Some see them as profound insights into reality's nature. Others dismiss them as tautologies disguised as explanations. They explain nothing, critics say, just restate observations. In multiverse theories, the anthropic principle gains explanatory power. If countless universes exist with varying constants, we necessarily find ourselves in one permitting observers. Our universe's properties aren't miraculous, but selected. Without multiverses, the apparent fine-tuning remains mysterious. Why this universe with these constants, capable of producing stars, planets, and beings who wonder about their own existence? Your existence too depends on countless contingencies, selection effects, and improbable circumstances. That you're here contemplating sleep rather than not existing is itself a kind of anthropic selection. Mystery 91. The WOW Signal. On August 15, 1977, a radio telescope detected a strong narrowband signal lasting 72 seconds. Astronomer Jerry Eamon circled it on the printout and wrote, "Wow." The signal came from the direction of Sagittarius, bore characteristics of artificial origin, and never repeated. Was it aliens? Probably not. The signal's frequency near the hydrogen line, a protected frequency band, and its failure to repeat despite extensive follow-up suggest a natural but unusual astronomical phenomenon or terrestrial interference, but we can't be certain. No natural explanation fully satisfies all the signal's properties. It remains a tantalizing mystery, the best SETI candidate ever detected, now lost to time. Thousands of other candidate signals have been detected and dismissed. Most prove to be interference, satellite communications, trolls, or mundane sources. The WOW signal stands alone in being both compelling and unexplained. We may never know its origin. Without repetition, confirmation is impossible. It remains a signal moment in SETI history, a reminder that the universe occasionally speaks to us in voices we struggle to interpret. Signals arrive at consciousness's edge, strange thoughts, hypnagogic imagery, the brain's wow moments as neural activity reorganizes for sleep. Most are noise, but occasionally something unprecedented appears. Mystery 92, Tabby's Star. KIC 8462852, nicknamed Tabby's Star, after astronomer Tabitha Boyajian, shows bizarre brightness variations. It dims irregularly and unpredictably, sometimes by up to 22%, far too much for planetary transits. The most exotic explanation proposed was a Dyson swarm, megastructures, built by advanced aliens to harvest stellar energy. While exciting, this explanation faced challenges. Follow-up observations showed the dimming is wavelength dependent, suggesting dust rather than solid objects. The current best explanation involves circumstellar dust from comets or disrupted planetesimals. But mysteries remain. The dust origin, the timing of events, and unusual long-term dimming trends all require explanation. Tabby's Star reminds us that the universe contains phenomena we haven't cataloged. Stars can behave in unexpected ways. Most anomalies have natural explanations, but finding those explanations requires careful observation and creative thinking. The excitement around potential alien megastructures, while premature, demonstrates humanity's eagerness to find cosmic companions. We search the skies hopefully, interpreting anomalies optimistically, longing for contact. Your thoughts dim irregularly now, brightness varying unpredictably, internal obscuration blocking consciousness's light as sleep's dust clouds gather. Mystery 93, Oumuamua. In October 2017, astronomers discovered the first confirmed interstellar object passing through our solar system. Named Oumuamua, Hawaiian for Scout, it showed peculiar properties that sparked debate. Its highly elongated shape, 10 times longer than wide, was unusual. More puzzling was its non-gravitational acceleration as it left the inner solar system, as if something was pushing it. The leading explanation is outgassing, cometary jets providing thrust as ice vaporizes. But Oumuamua showed no visible coma or tail. Alternative proposals included it being a hydrogen iceberg, a nitrogen ice fragment, or even a light sail built by aliens. The alien hypothesis, proposed by Harvard astronomer Avi Loeb, remains controversial. Most scientists favor natural explanations, though none perfectly fit all observations. Oumuamua is now far beyond reach, too distant for further study. Its mysteries will likely remain unsolved unless similar objects visit and we observe them more carefully. The discovery proved that interstellar objects pass through regularly. As survey telescopes improve, we'll detect more, perhaps answering questions raised by this first enigmatic visitor. Strange visitors arrive at the borders of sleep, thoughts from unknown origins accelerating inexplicably through consciousness before departing into the outer darkness of unconsciousness. Mystery 94. Ultra-high energy cosmic rays. Cosmic rays, high-energy particles from space, bombard Earth constantly. Most have energies explainable by supernova acceleration. But occasionally, particles arrive with energies so extreme they shouldn't exist. Ultra-high energy cosmic rays carry energies exceeding 10 to the power of 20 electron volts, equivalent to a baseball traveling 60 miles per hour, concentrated in a single atomic nucleus. At such energies, they should interact with cosmic microwave background photons and lose energy rapidly, preventing travel from distant sources. This is the GZK cutoff, named after physicists who predicted it. Yet we detect particles above this limit. How do they reach us? Possible sources include nearby exotic objects, gamma-ray bursts, active galactic nuclei, or unknown phenomena producing these energies. Or perhaps the particles don't travel far but are created locally by new physics. Another possibility, the GZK cutoff isn't absolute. New particles or interactions might allow higher energies than predicted. These cosmic rays might be revealing physics beyond the standard model. Each detection is precious. They're extraordinarily rare. Building detectors large enough to catch sufficient numbers for statistical analysis requires vast arrays covering thousands of square kilometers. Particles of thought arrive with varying energies, most low and manageable, but occasionally one strikes with startling intensity before sleep's atmosphere absorbs all such high-energy intrusions. Mystery 95. The Pioneer Anomaly. NASA's Pioneer 10 and 11 spacecraft, launched in the 1970s, experienced tiny, unexplained accelerations toward the Sun. The Pioneer anomaly puzzled scientists for decades. The acceleration was minuscule, about 10 trillionths of a meter per second squared, but consistent and unaccounted for. Proposed explanations ranged from modified gravity theories to dark matter halos to systematic errors in tracking. Eventually, careful analysis revealed the likely cause: anisotropic thermal radiation. The spacecraft's radioactive power sources emitted heat, and this heat, radiating preferentially in certain directions, created a tiny rocket effect. The anomaly's resolution demonstrated science working properly. A mysterious observation received serious attention. Multiple hypotheses were tested, and the prosaic explanation eventually prevailed. But the episode shows how difficult space navigation really is. Tiny, subtle forces affect spacecraft motion. Accounting for all influences requires painstaking attention to detail. The Pioneer anomaly also sparked research into alternative gravity theories and motivated more precise tests of general relativity in the outer solar system. Anomalies in your trajectory toward sleep, sudden jerks, hypnic jerks, brief accelerations back toward waking, arise from neural thermal radiation, random firing patterns creating tiny perturbation. Mystery 96, the cold spot. In the cosmic microwave background, there's a region about 70 times the moon's diameter that's cooler than its surroundings, the cold spot. It shouldn't exist according to standard cosmological models. Statistical analysis suggests it's too large and too cold to be a random fluctuation. So what caused it? One possibility is a supervoid, an enormous underdense region of space that photons cross, becoming cooler through the integrated Sachs-Wolf effect. But even supervoid explanations require unusually large or underdense structures. Alternative ideas include it being a remnant of pre-Big Bang physics, evidence of bubble universe collisions, or topological defects from phase transitions in the early universe. The cold spot might be pure chance. With enough sky to analyze, even improbable features sometimes appear. Calling it anomalous might be cherry-picking, focusing on one unusual region among many possible regions. Future observations with better resolution and sensitivity might reveal the cold spot structure in more detail, potentially resolving its origin. Or it might remain a cosmic Rorschach test, ambiguous enough to support multiple interpretations. Cold spots appear in the thermal map of consciousness, regions unexpectedly quiet, underdense in thought, strange voids in the normally uniform background of awareness. Mystery 97. The Lithium Problem. Big Bang nucleosynthesis predicts how much hydrogen, helium, and lithium formed in the first few minutes after the Big Bang. Observations match predictions for hydrogen and helium perfectly, but lithium is wrong. The oldest stars contain only about 1/3 the lithium predicted by theory. Where did the missing lithium go? Stars might destroy it through nuclear reactions, or perhaps our understanding of Big Bang nucleosynthesis is incomplete. Some proposals invoke new particles or forces in the early universe that affected lithium production. Others suggest lithium was destroyed in stellar interiors, more efficiently than we think, then mixed throughout stars. Or maybe our measurements are wrong. Determining lithium abundance in old stars is technically challenging, and systematic errors might explain the discrepancy. The lithium problem is one of the few clear contradictions between Big Bang theory and observation. Solving it might reveal new physics, or might simply improve our understanding of stellar evolution and chemical mixing. It's a reminder that even our most successful theories, Big Bang cosmology has successfully predicted countless observations, still have loose ends requiring explanation. Loose ends in consciousness unravel as sleep approaches, predictions and memories failing to match perfectly, small discrepancies accepted rather than explained. Mystery 98. Irregular galaxies. Most galaxies are either spiral or elliptical, but about a quarter show no clear structure. Irregular galaxies, chaotic and disorganized. What makes them different? Many irregulars are small dwarf galaxies, too small for gravity to organize them into spiral arms or elliptical smoothness. Others are galaxies distorted by collisions or tidal interactions with larger neighbors. The large and small Magellanic Clouds, satellite galaxies of the Milky Way, are irregulars. Their structures were disrupted by tidal forces during close passages of our galaxy. But some irregulars don't fit these explanations. They're large enough and isolated enough that they should have organized structures, yet they don't. What prevented their organization? Irregular galaxies often have active star formation, with young stars scattered throughout. This suggests recent disturbances, or ongoing gas accretion fueling star birth. Understanding irregular galaxies helps us understand galaxy evolution generally. They might represent transitional stages, galaxies caught in the process of transformation from one type to another. Thoughts become irregular as sleep approaches, organization dissolving, structure fragmenting, the spiral arms of logic scattering into chaotic star-forming regions of dream. Mystery 99. Galaxy alignment. Large-scale surveys reveal that galaxy rotation axes aren't randomly oriented. In some regions, galaxies align, their spins preferentially pointing in similar directions. This alignment extends over hundreds of millions of light years, far larger than any direct interaction between galaxies could explain. Something about cosmic structure formation produces these correlations. The leading explanation involves primordial tidal fields. As cosmic structure formed, the same tidal forces that shaped large-scale structure also influenced how galaxies accreted gas and began rotating. Galaxies forming in similar environments acquired similar spins, but the details remain murky. The strength and scale of observed alignments challenge some models. Whether dark matter plays a role, and how galaxy formation couples to large-scale tidal fields requires better understanding. Galaxy alignment also affects weak gravitational lensing studies. When measuring how mass distorts space-time by bending light, you must account for galaxy orientations not being random. These cosmic choreographies, galaxies waltzing in alignment across vast distances, reveal the universe's interconnectedness, its ability to maintain correlations across seemingly impossible scales. Your thoughts align with sleep's tidal forces now spinning down, axes reorienting toward unconsciousness, all mental processes acquiring similar orientations toward rest. Mystery 100, the universe's ultimate fate. How will the universe end? Current evidence suggests continued expansion, accelerating forever due to dark energy. This leads to the big freeze or heat death. As expansion continues, galaxies recede beyond each other's cosmic horizons. Eventually, our local group of gravitationally bound galaxies will be completely isolated, surrounded by darkness as all other galaxies disappear beyond light-speed recession. Stars will exhaust their fuel. The last stars will burn out in 100 trillion years. White dwarfs will cool to black dwarfs. Neutron stars will dim. Black holes will evaporate via Hawking radiation over unimaginably long timescales. Eventually, even protons might decay, leaving only photons, neutrinos, and black holes. Then, after 10 to the power of 100 years, the last black holes evaporate, and the universe becomes truly empty, a cold, dark, featureless void approaching maximum entropy. Alternative fates exist if dark energy evolves. Phantom energy could cause a big rip, tearing apart galaxies, stars, planets, atoms, and finally space-time itself. Or dark energy might weaken, allowing gravity to reverse expansion in a big crunch. The universe might be cyclic, with big bangs following big crunches eternally. Or quantum tunneling might trigger vacuum decay, destroying the universe in an expanding bubble traveling at light speed. We don't know how the story ends. The final chapter remains unwritten. The universe's ultimate fate is mysterious as its origin, the Alpha and Omega both hidden in uncertainty. But tonight your personal universe doesn't end. It merely pauses, consciousness cycling down for maintenance, preparing for tomorrow's continuation, your own small story persisting through the night. And so we complete our journey through 100 mysteries of the universe, from the largest structures to the smallest quantum fluctuations, from the beginning of time to its ultimate end, from dark matter to consciousness itself. We've touched on the greatest questions that occupy human minds. But notice how you feel now. These mysteries don't burden you. They don't demand solutions. Instead, they invite wonder, perspective, calm. Each unsolved question reminds us that reality is far richer and stranger than we imagine. The universe doesn't require our understanding to be magnificent. It spins on through the darkness, stars being born and dying, galaxies dancing their gravitational waltz, quantum foam bubbling beneath space-time's surface, all without needing our comprehension or approval. And you too don't need to understand everything to rest peacefully. Your consciousness doesn't require explanation to function. Your dreams need no theoretical framework to unfold. Sleep comes whether you understand it or not. As you drift now into that mysterious state between waking and sleeping, imagine yourself floating in the vast cosmic ocean. Above you, the galaxies spiral slowly. Below you, quantum fluctuations shimmer. Around you, dark matter and dark energy hold everything in balance. You're made of star stuff, as Carl Sagan said. Every atom in your body was forged in stellar furnaces or created in the Big Bang itself. You're not separate from these cosmic mysteries. You're part of them, a way the universe has organized itself to contemplate its own existence. Let your breathing slow like the expansion of space itself, steady, inevitable, requiring no effort. Let your thoughts dim like stars receding beyond the cosmic horizon, their light stretched to invisibility by expansion. The mysteries remain mysteries, the questions remain questions, and that's perfect. Some things are meant to be wondered about, not solved. Some questions are more valuable than their answers could ever be. Sleep now, cosmic traveler. Rest among the mysteries. Dream of universes within universes, of possibilities and probabilities, of quantum superpositions and gravitational waves. Or dream of nothing at all. That's a mystery too, and equally beautiful. The universe holds you gently, as it holds every particle and planet, every star and galaxy. You're supported by forces older than time, cradled by the fabric of space-time itself, rocked to sleep by the gentle rhythm of cosmic expansion. Everything is mystery, everything is wonder, and in this wonder there is profound peace. Good night, traveler. The cosmos watches over you as you sleep.